On the 10th of April, a capsule fell toward Earth at 24,000 miles an hour. 4 people were inside it, and the air ahead of them reached 5,000 degrees. For 2 years, every argument about that flight had been about one thing: the heat shield. It worked, and it worked better than almost anyone expected. What did not work was a valve buried in a module nobody was watching. It leaked helium 10 times faster in space than it ever did on the ground, and that valve no longer exists anywhere in the universe. So here is the question underneath everything that follows. Can engineers repair a machine they are never permitted to examine? Subscribe and tell me in the comments where you are watching from tonight. Let's get into it. Part 1. The half second everyone was watching. Coming home from the moon is not the same as coming home from orbit. A capsule returning from the space station is moving at 17,500 miles an hour. A capsule returning from lunar distance has fallen down a far deeper gravity well. It arrives at somewhere between 24 and 25,000 miles an hour. The energy you must destroy scales with the square of that speed. This is not a small difference in degree. This is a different physics problem entirely. You get rid of that energy by turning all of it into heat. You survive it by putting something in front of you designed to be destroyed. The material on Orion's heat shield is called Avcoat, and it is ablative. It is not built to resist heat, and it is not built to last. It is built to char, break apart, and carry the heat away as it goes. The shield is supposed to be partially consumed on every flight. That is not damage. That is the design working exactly as intended. The capsule was named Integrity, and the crew chose that name themselves. It struck the discernible atmosphere roughly 75 miles above the Pacific Ocean. At that moment it was moving about 5 times the speed of sound. The compressed air in front of the shield climbed to around 5,000 degrees Fahrenheit. That is close to half the temperature of the visible surface of the Sun. 2 drogue parachutes deployed first to stabilize the falling capsule. 3 pilot chutes followed, and those pulled out 3 main parachutes. Each main canopy measures 116 feet across when fully inflated. Together they slowed Integrity from hundreds of miles an hour to about 17. That is roughly the speed of a bicycle coasting downhill on a quiet street. Splashdown came at 7 minutes past 8 in the evening, Eastern Time. The date was the 10th of April, and the location was the Pacific off San Diego. The capsule landed 2.9 miles from the exact point NASA had targeted. Its velocity when it touched the atmosphere was within 1 mile an hour of prediction. I want you to hold that second figure, because it is genuinely remarkable. Not within 1%, within 1 mile an hour, after a journey of several 100,000 miles. The models describing that re-entry were essentially perfect. The recovery ship was the USS John P. Murtha, and it was waiting nearby. United States Navy divers were in the water within minutes of the splash, and before the capsule was even lifted from the ocean, those divers did something unusual. They swam underneath it and photographed the heat shield in place. Think about why that mattered enough to do it immediately, in open water, before recovery. 2 years of institutional anxiety had been aimed at that single surface. Nobody wanted to wait for a hangar in Florida to find out. The photographs came back, and the shield looked good. Commander Reed Wiseman described it afterward in plain language. He said there was a little char loss on what is called the shoulder. Then he said they leaned under and looked at the bottom of the thing. He said it looked wonderful to them. NASA published its initial post-flight assessment on the 20th of April. The thermal protection system performed as expected, with no unusual conditions identified. char loss was significantly reduced compared to the previous flight in both quantity and size. The behaviour matched what ground testing had predicted after the last mission. So the story appears to end well, right there in the water off San Diego. The thing everybody feared did not hurt anybody. The engineers were right, the fix worked, and 4 people walked away from it. Except that during those same 10 days, in a different part of the same spacecraft, something else was happening. A system almost nobody outside the program was watching was quietly behaving in a way nobody had predicted. It left no visible mark and triggered no alarm. It showed up only as a number on a gauge. And to understand why nobody was watching that number, you first have to understand what they were watching instead. That begins with a record that had stood since before most people alive today were born. Part 2. The record that stood for 56 years. On the 1st of April, at 6:35 in the evening Eastern Time, the Space Launch System rocket lifted off. The pad was Launch Complex 39B at the Kennedy Space Center in Florida. On top of that rocket sat the Orion spacecraft the crew had named Integrity. There were 4 people aboard. Reed Wiseman commanded the mission. Victor Glover flew as pilot. Christina Koch and Jeremy Hansen served as mission specialists. Hansen belongs to the Canadian Space Agency, and he made history simply by strapping in. He is the first person who is not an American ever to fly a lunar mission. They were also the first human beings to leave low Earth orbit since December of 1972. 53 years and 4 months separated Apollo 17 coming home from that rocket, leaving the pad. 2 entire generations of engineers had been born, trained and retired inside that gap. Now the flight profile matters enormously here, so let me be precise about it. Artemis II was not a landing, and it was not even an orbit of the moon. It flew what engineers call a free return trajectory, and the name describes it exactly. You throw the spacecraft at the moon along a very carefully calculated path. The moon's own gravity then swings it around and flings it back toward Earth. The critical property is what happens if everything else fails. If every system on board dies, the laws of orbital mechanics still carry you home. You do not need to fire an engine to escape the moon. Gravity has already been arranged to do that work for you. I want you to hold that fact about the free return in your mind. It is going to come back later and explain a decision that seems strange until you understand it. The main engine on Orion fired exactly once during the entire mission. That single burn is called translunar injection, and it set the whole path. Every course adjustment after it was handled by much smaller thrusters. The big engine was started, it did its job, and it was never needed again. On the 6th of April, at roughly 2 minutes past 7 in the evening Eastern, something happened aboard that spacecraft. Integrity reached a distance of 252,756 miles from Earth. That number broke a record which had stood since 1970. Apollo 13, on its crippled loop around the far side of the moon, carried 3 men to 248,655 miles. That figure had held for 56 years, and it had held because of a disaster. Artemis II beat it by 4,101 miles. 4 people had never been that far from home. In the entire history of our species, nobody had ever been that far away. There is a second number that appears constantly in coverage of this flight. NASA's official figure for the total journey is 694,481 miles. That is not the distance from Earth, and the two are confused everywhere. That is the total distance travelled, out and back, along the whole curving path. When you see those figures used interchangeably, one of them is being used wrong. The crew looped the far side of the moon and watched Earth rise over the lunar horizon. Roughly 24 human beings in history have seen that with their own eyes. They photographed it through the windows. They named a crater. They spoke to the president from lunar distance. Then physics did what physics does and brought them back. The full mission ran 9 days, 1 hour and 32 minutes. By almost every measure that mission planners care about, it was close to flawless. Entry velocity within 1 mile an hour. Landing within 3 miles of target. Crew home safe. And yet a quiet anomaly rode home in the telemetry, in a system that had never been the subject of a single news cycle. Before I can show you what it was, I have to show you what consumed all the attention. That story starts on a November afternoon in 2022, with a spacecraft that came home carrying evidence of something nobody had planned for. Part 3, the shield that broke itself from the inside. Take yourself back to the 16th of November, 2022. That flight was Artemis I. Same rocket design, same spacecraft design, no crew aboard. It was the uncrewed test flight, and its purpose was to find what breaks. You fly it empty precisely, so you can discover problems without killing anyone. By the standard the program set for itself, it succeeded completely. Then engineers pulled the capsule apart and examined the heat shield. NASA's own Office of Inspector General described what they found, and the wording carries the whole story. NASA identified more than 100 locations where the ablative material wore away differently than expected. It cracked and broke off the spacecraft in fragments, creating a trail of debris. It did not melt away as it had been designed to do. Consider what that sentence actually describes. Not smooth erosion, which is the design intent. Fragmentation, pieces of protective material departing the vehicle at hypersonic speed, above a compartment that would, on the very next flight, contain 4 living human beings. There is a second danger inside that finding, and it gets underplayed constantly. A shield that sheds chunks is not only a thermal problem. Those fragments have to travel somewhere in a hypersonic airflow. They move down the body of the capsule past the forward bay cover. That bay contains the parachute system. Now hold that image for a second, because it reframes everything. A liberated piece of heat shield striking a parachute pack would make the shield's thermal performance completely irrelevant. You would have a perfectly protected capsule descending at several hundred miles an hour. The quality of your heat shield stops mattering when your canopies do not open. So NASA opened an investigation, and that investigation consumed roughly 2 years. Stay with me here, because the answer they reached is genuinely elegant. It also explains a decision that gets misreported almost every time it is described. Avcoat is not perfectly uniform material. When it heats, it generates gases inside itself as it chemically breaks down. That process is called pyrolysis, and it is entirely normal. Those gases have to escape outward through the material as it chars. The property governing whether they can escape is called permeability. What engineers found was that permeability varied from place to place across the shield. In some regions the material was more porous and gas escaped easily. In other regions it was tighter, and the gas had nowhere to go. Amit Kshatriya is NASA's Associate Administrator, and he is central to this entire story. He explained the finding in December of 2024. He said the heat shield was not uniform in terms of permeability. There were places where it was more permeable than the rest. In exactly those places, they did not see in plain cracking. That is the fingerprint of the failure, and it is unmistakable. Where gas could vent, the shield behaved perfectly. Where gas could not vent, pressure built up inside the material itself. Here is the version you can feel in your hands. Picture a sealed container of something wet going into a very hot oven. If the steam inside can escape, you get an even, predictable result. If the steam is trapped, pressure builds until something splits open. The shield was not being torn away by the airflow outside it. The shield was breaking itself apart from within. But there was a second half to that finding, and it changed the entire program. The reason pressure had time to accumulate was the flight path itself. Artemis I flew what is called a skip entry. The capsule dips into the atmosphere and sheds some speed. Then it skips back upward, like a flat stone across water. Then it comes down again for the final descent. It is a genuinely clever maneuver with a real operational benefit. It gives you far more control over your landing point, which means you can put a crew down near a waiting ship. The skip carries a cost though, and that cost is time. During the skip, the shield experiences a cooling phase between two separate heating phases. It was inside that cooled down that trapped gases found the conditions to build pressure and crack the char. So a 2-year materials investigation produced a fix involving no new material at all. The fix was to fly a different path. That decision is entirely legitimate engineering, and I want to say so clearly. It is also the kind of decision that makes a certain type of engineer deeply uncomfortable. You have not eliminated the flaw in the material. You have arranged the mission so the flaw never gets fully exercised, and at least one former astronaut who had flown the first shuttle mission after Columbia considered that distinction unacceptable. He put his objection in writing, addressed to the administrator weeks before launch. Part 4. The astronaut who told NASA not to fly. Dr. Charlie Kamada is not an outsider throwing rocks at an agency. He is a former NASA astronaut and a career engineer specializing in thermal protection systems. That specialization matters enormously to what follows, and there is one line on his record that gives his objection unusual weight. Kamada flew on STS 114. That was the very first space shuttle mission after the loss of Columbia. He rode a vehicle whose entire flight rationale was a return to flight investigation. He has personally stood where this program was standing. He has flown hardware that an agency declared safe after a fatal accident. That experience is why people listened when he objected. Kamada argued publicly that NASA should not fly the existing shield design with people aboard. He called the plan crazy in interviews. He said the agency kept kicking the can down the road on the underlying problem. His technical objection was specific rather than emotional. He argued NASA had not performed a validated, integrated multiphysics analysis of the char loss. He wanted independent reviewers brought in from entirely outside the agency. He suggested the Department of Energy, or academic institutions, or anyone whose career did not depend on the launch schedule. In January of this year, he sent an open letter to Administrator Jared Isaacman. In it, he wrote that accidents occur when organizations convince themselves they understand problems they do not. He wrote that this issue exhibited the same patterns that preceded past catastrophes. I want you to hold that claim, because we are going to test it directly. Later in this story, we will walk through 3 actual catastrophes in detail. You will be able to judge for yourself whether the pattern he described was really present here. Kamada was not alone, though the others landed in different places. Danny Olivas is another former astronaut who shared the concerns publicly. He went through the same review process Kamada did. Olivas came away satisfied after being briefed by what NASA called a Tiger team. That difference matters more than it might appear. 2 people with comparable backgrounds examined the same data and reached opposite conclusions. That is not evidence of a cover-up or of incompetence anywhere. That is what a genuinely difficult engineering judgment looks like from inside. Dan Rasky is a veteran of thermal protection work, and he offered the most quotable assessment of the whole affair. He said that with spalling, you are right at the point of incipient failure. Then he described it as being at the edge of a cliff on a foggy day. Sit with that image, because it is doing precise technical work, He is not claiming you will fall off the cliff. He is claiming you cannot see how much ground remains between you and the edge. That is a fundamentally different warning than a prediction of disaster. It is a warning about margin, and specifically about unmeasured margin. Engineers do not primarily fear failure. They fear not knowing how close to failure they currently are. The descent was not confined to individuals. Either, in May of 2024, NASA's Office of Inspector General published a formal report. Its title was NASA's Readiness for the Artemis II crewed mission to lunar orbit. Inside it, the Inspector General wrote that Artemis I revealed anomalies with the Orion heat shield. It named the separation bolts and the power distribution system alongside it. Then it stated those anomalies posed significant risks to the safety of the crew. Significant risks to the safety of the crew. That is not a journalist's phrasing chosen for drama. That is the agency's own internal watchdog in an official document 2 years before launch. The same report contained a number worth hearing precisely. By the launch date then planned, NASA would have spent more than $55 billion. That figure covers the Space Launch System, Orion, and the associated ground systems together. $55 billion committed, a written crew safety warning from the Inspector General, a former astronaut publishing an open letter, a thermal protection veteran describing a foggy cliff edge. That was the environment in which one man had to make a decision. He gave himself half a day to make it, and what happened in that room determined whether 4 people flew. Part 5. The half day that decided everything. In January of this year, NASA Administrator Jared Isaacman convened a review. It ran for half a day, and its scope was deliberately narrow. The question was whether Orion should fly with the existing heat shield. The room was not filled with people who would agree with each other. It included the agency's senior human spaceflight leadership. The chair of the independent review team attended. Outside experts were brought in, and both Kamada and Olivas were among them. That detail deserves recognition. The administrator put his loudest public critic in the room and let him make his case directly. Afterward, Isaacman issued a public determination. He said the agency had full confidence in the Orion spacecraft and its heat shield. He grounded that confidence in rigorous analysis and the work of exceptional engineers who followed the data. Then he added a second sentence that most coverage skipped past. He said they had modified the re-entry profile and that they had regained margin to safety. Read the structure of that sentence carefully, because it concedes something. Regaining margin means margin had previously been lost, and it locates the recovery of that margin in the flight path rather than in the hardware itself. Now, the engineering case underneath that decision was stronger than most coverage conveyed. I do not want to leave you with the impression that confidence was manufactured. The analysis examined a genuine worst-case scenario. Suppose the Avcoat blocks were stripped entirely from the shield during descent. Beneath those blocks sits a thick composite structure built on a titanium framework. The engineers concluded that structure alone could still protect the people inside. That is a real argument, and it has a name in safety engineering. It is called defense in depth. You do not rely on the outer layer performing perfectly, because you have another layer beneath it. There is one more correction I need to make here, because it is reported wrong almost universally. Many outlets said NASA abandoned the skip entry entirely and flew a direct re-entry instead. That is not accurate, and the distinction genuinely matters. Kshatriya described what they actually did. He said they were still doing a skip entry. Then, he said they had shortened the duration of the skip because of the limited duration of this heat shield. Shortened, not eliminated. Less time in that cool-down phase between heating pulses. Less time for gas to accumulate inside the material and crack it. There is reporting that the horizontal target line was pulled inward for this purpose. The figures given are around 2,300 nautical miles, reduced to roughly 1,700. I have not been able to trace that specific pair of numbers to a NASA transcript, so I will tell you it is reported rather than confirmed, and you should hold it loosely. The essential point survives regardless of those exact figures. They did not repair the material. They flew a path that gave the material less opportunity to fail, and then they launched, and the shield came home in good condition. I want to be completely clear about that outcome, because it would be easy to imply NASA got lucky. The data does not support that framing at all. The post-flight char loss was consistent with ArcJet ground testing conducted after Artemis I. The models predicted this result, and the flight delivered exactly what the models predicted. Wiseman looked underneath the capsule himself in the water. He said the bottom looked wonderful to them. That is a commander's assessment of the surface that stood between his crew and 5,000 degrees. The 2-year investigation produced a correct answer. The descent produced a genuine review rather than a rubber stamp. The administrator's confidence turned out to be justified by events. Everything visible worked, and it worked because an enormous quantity of attention was pointed directly at it. Which raises a question that took me a long time to shake. What was happening during those same 10 days? In the parts of that spacecraft where nobody was pointing anything at all? Part 6. The number nobody was watching. There was a helium leak aboard Artemis II. Before I explain what that means, I need to clear up a misconception. Early reporting got this wrong in a way that made it sound both more frightening and less interesting than it is. This was not a leak of the air the crew were breathing. Some initial coverage implied an oxygen supply problem affecting life support. NASA specifically clarified that this was not the case at all. Nobody's breathing air was ever escaping anywhere. The helium in that spacecraft is not for breathing. The helium is for pushing. Let me walk you through how Orion's propulsion system actually works. Once you see the architecture, everything that follows becomes obvious. Orion has 2 main pieces joined together in flight. There is the crew module, the cone-shaped capsule holding the people. That is the piece that comes home. Behind it sits the European service module, and that is where nearly everything else lives. Power, water, air, thermal control and propulsion all belong to the service module. The propulsion system burns what are called hypergolic propellants. That term means 2 chemicals which ignite spontaneously the instant they touch. There is no spark plug anywhere in the system. There is no igniter to fail on the far side of the moon. You open 2 valves, the chemicals meet, and combustion begins immediately. This is old technology, and it is used precisely because almost nothing in it can fail. The fuel is monomethylhydrazine. The oxidizer is a compound of nitrogen and oxygen called nitrogen tetroxide. But you still have to move those liquids from their tanks into the engine. An aircraft would use a pump, and pumps have moving parts that break. This spacecraft uses pressure instead, which has almost no moving parts at all. You store a supply of gas at extremely high pressure in separate tanks. That gas squeezes the propellant tanks and forces liquid down the lines toward the engines. Engineers call that gas the pressurant. On Orion, the pressurant is helium. Now Jeff Radigan served as lead flight director for this mission. He described the anomaly more precisely than anyone else has managed. He said the leak is not to space, and that it is internal to the system across some of their valves. He added that they really needed to characterize it to determine what modifications might be required. That phrase, not to space, carries enormous weight. Nothing was venting into vacuum. No plume was visible from any camera. There was no external sign whatsoever that anything was wrong. This was helium slipping past valves inside a sealed system, on the oxidizer side of the plumbing. Pressure moving somewhere it was not supposed to go, deep inside a closed machine. The only way anyone could perceive it was by watching gauges. There was no bang and no alarm that woke the crew from sleep. There was a set of numbers that did not match the numbers anyone expected. And here is the first genuinely uncomfortable fact in this entire story. They already knew about it. Kshatriya confirmed publicly that managers were aware of a low leak rate before launch. Not discovered in flight, known on the ground, documented, and reviewed before those 4 people climbed aboard. A similar leak had appeared on the uncrewed Artemis I flight back in 2022. It was a known characteristic of this hardware, and it had been formally accepted as flight-worthy. Now I want to be scrupulously fair about the reasoning behind that acceptance. It was not lazy, and it was not a case of anyone shrugging off a warning. Remember the free return trajectory from earlier. Remember that I asked you to hold it. This mission was deliberately designed so the main engine fired only once. After translunar injection, the moon's gravity performed all the remaining work. Every course correction afterward used small thrusters, and those thrusters do not depend on the helium system to recharge their pressure. The propulsion system was never going to be asked to perform near its limits, so the review examined a small helium leak on a mission that barely used propulsion. It concluded the leak did not matter for this flight, and that conclusion was correct. Nothing about that leak endangered those 4 people. The crew was never at risk from it at any point. I want that stated plainly, because the rest of this is not a story about a near miss. But then they flew, and for the first time they measured that leak in space. Kshatriya's description of what they found is the sentence this whole story turns on. He said the leak rate they saw in flight was an order of magnitude higher than what they had seen on the ground. He added that it was still acceptable. Then he said it would probably lead them to an extensive redesign of that valve system. An order of magnitude means roughly 10 times, not 10% worse than expected. 10 times worse. Let me put that in terms you can feel immediately. Imagine a car rated at 40 miles per gallon on the test track. Then imagine driving it in the real world and getting 4. You would not call that a modest measurement discrepancy. You would conclude the test track had been telling you something false about the world. That is precisely what happened here. The ground testing was not slightly imprecise about this valve. By a factor of 10, it was not describing how the hardware behaves where it actually operates. Which raises the obvious question, and the answer is stranger than most people expect. Why would a valve behave one way in a laboratory in Germany and another way entirely in space? The answer lives in the peculiar physics of the one element that will not stay where you put it. Part 7. The gas that will not stay in a box. Why helium specifically? There are 2 good reasons, and both of them matter. The first is chemistry, or rather the complete absence of it. Helium is a noble gas, which means it does not react with anything. Your pressurant sits in direct contact with propellants that are desperate to react with almost anything. Nitrogen tetroxide will attack most materials given the slightest opportunity. You need a gas that will sit next to it for weeks and do nothing at all. The second reason is temperature. Helium stays a gas at extraordinarily low temperatures, far below anything a spacecraft encounters. A pressurant that condenses into liquid inside your plumbing is worse than useless. It stops pushing at the exact moment you need pressure most. So helium is very nearly the perfect substance for this job. And it has a third property that turns it into a permanent problem. A helium atom is the smallest practical thing you can attempt to contain. It is a single atom rather than a molecule of bonded atoms. It is chemically inert, so it will not stick to anything as it travels. And it is tiny beyond ordinary intuition, which means helium will escape through a seal that would hold any other gas perfectly for years. Picture a woven basket in your hands. It will hold gravel indefinitely without losing a single stone. It It will hold dry sand for quite a while before it starts trickling out. It will not hold water for even a moment. The basket is not badly made in any of those three cases. The basket is identical each time. What changes is the size of the thing you asked it to contain. Helium is the water. Every valve seat and every seal in every propulsion system has microscopic imperfections. Most gases never find those gaps, and never will. Helium finds all of them. Keep that basket in your mind, because we are going to come back to it. It explains something important about a different spacecraft, built by a different company, on a different continent. This is why helium leaks are not a NASA problem or a Boeing problem. They are a physics problem that everyone in this industry keeps colliding with. The Space Launch System rocket itself required helium valve replacements before both Artemis launches. SpaceX has scrubbed flights over valve issues of its own. Nobody has solved this. Nobody is going to solve it, because the difficulty is built into the periodic table. But that still leaves the puzzle from the previous part unanswered. Why would this specific valve leak 10 times worse in space than in a laboratory? The answer is that a laboratory in northern Germany cannot reproduce the conditions of a lunar trajectory. Not fully, and possibly not at all. Consider what that hardware actually experiences once it leaves Earth. One side of the spacecraft faces the sun directly, with no atmosphere to moderate anything. The opposite side faces empty space at temperatures approaching absolute zero. There is no air to carry heat from the hot side to the cold side. Metal expands when heated and contracts when chilled. Every component in that valve is made of materials with slightly different expansion rates. A seal compressed perfectly at room temperature may not remain compressed after that cycle. Then the spacecraft rotates, and the hot side becomes the cold side. Then it rotates again. The hardware is being flexed continuously, gently, in ways no static ground test replicates. So the flight was not a confirmation of the ground testing. The flight was the first honest test that Valve had ever been given. And the flight was also, by design, the final few days of that valve's existence. To understand why, you need to see the machine it was living inside. It is far stranger and far larger than most people realize. Part 8. The engines that used to fly the space shuttle. When you picture Orion, you almost certainly picture the cone. The capsule with the windows and the people, the shape that has barely changed since Apollo. That cone is the smaller half of the spacecraft, and it does the least. Behind it sits a cylinder roughly 13 feet across. That is the European Service Module, and it is where the spacecraft actually lives. It carries the propellant and the engines. It generates all the electricity. It holds the water and the oxygen, and manages the heat. Strip that module away, and the crew module becomes a metal cone with seats. It can fall, and it can survive falling. It cannot go anywhere or keep anyone alive for long. That module is built by Airbus in Bremen, in northern Germany, under the leadership of the European Space Agency. 20 main contractors work on it. More than 100 suppliers contribute, spread across 13 European countries. Let me put that another way, because the scale gets lost in the numbers. 13 nations coordinate their industrial output to build one component of one American spacecraft. It is one of the most internationally distributed pieces of engineering ever flown with humans aboard. 4 solar arrays unfold from that cylinder once it reaches space. They span roughly 62 feet from tip to tip when fully deployed. They carry approximately 15,000 individual solar cells across their surfaces. Together, they generate around 11 kilowatts of electrical power. The module carried about 90 kilograms of oxygen for the crew to breathe. It carried roughly 240 kilograms of water. On Artemis II, it propelled the spacecraft more than 1 million kilometers through space, and it carries 33 engines. One of those is the main engine, and there is a detail here worth pausing on. That main engine is a repurposed orbital maneuvering system engine from the Space Shuttle program. It is not a copy or a modern reproduction of one. It is an actual shuttle engine, pulled from inventory, refurbished, and bolted onto a new spacecraft. Engines that once nudged shuttles around low Earth orbit now push human beings toward the moon. I find that genuinely moving, and I want to say why. The shuttle program ended in 2011, and its hardware was scattered to museums. But some of it went into storage instead, and some of that storage is now flying to the moon. Around that main engine sit 8 auxiliary engines. Beyond those, 24 small attitude control thrusters allow the spacecraft to turn and hold orientation. 33 engines. 15,000 solar cells. 13 countries. More than 100 suppliers. Years of assembly in a hall in Bremen, with technicians working to tolerances measured in fractions of a millimetre. When the solar arrays were finally installed, one engineer on the program said Orion had its 4 wings and was good to fly. That is a person describing something they built with pride, and the pride is earned. This is not a simple machine assembled quickly. It represents a substantial fraction of European aerospace capability in one cylinder. Now hold all of that in your mind at once. The engines with shuttle heritage, the 15,000 cells, the 13 nations, the oxygen and the water and the plumbing. Every single Orion mission ends the same way for that module, and what happens to it is not an accident, or a loss, or a failure of any kind. It is the plan, and it has always been the plan, and it happens roughly 20 minutes before the crew comes home. Part 9. 20 minutes before home. At an altitude of approximately 122 kilometers, the two halves of Orion separate. That is around 400,000 feet above the ocean, still well above the atmosphere. The crew module turns its heat shield forward and begins its descent. It is protected, and it is aimed, and it is going home. The service module does not go home. It remains on its own trajectory, and it has no heat shield. It has no thermal protection of any kind, because it was never meant to need any. It enters the atmosphere unprotected at orbital velocity. It burns. It breaks apart. It is deliberately incinerated over the ocean, minutes behind the capsule it kept alive. The European Space Agency describes the outcome plainly in its own materials. The service module burned up harmlessly in Earth's atmosphere. Harmlessly is accurate in the sense they mean it. Nothing on the ground was endangered, and no debris threatened anyone. But sit with the other meaning of that word for a moment. Everything I described in the previous part existed for 9 days, and then stopped existing. The 33 engines, the plumbing, the tanks and the lines and the seals, and somewhere in that propulsion plumbing, on the oxidizer side, sat one particular valve. It was the only physical example in the universe of hardware that had just demonstrated a leak rate 10 times worse than predicted. That valve is not in a laboratory anywhere. It is not in a hangar in Florida awaiting analysis. It is not sitting on a shelf at Marshall Space Flight Center waiting for an X-ray machine. It is atoms, distributed across a wide stretch of the Pacific Ocean. Now I need to be careful here, because there is a dishonest version of this story. I am not going to tell you that version, and you should distrust anyone who does. The dishonest version says NASA lost the evidence through carelessness. NASA did not lose anything at all. The service module is expendable by deliberate design, for reasons that are completely sound. Building it to survive re-entry would require giving it a heat shield. That means structure and mass, and every kilogram of that mass comes directly out of your payload. It would make the spacecraft measurably worse at the thing it exists to do. Nobody made a mistake. This is the architecture, and Apollo used the same architecture, and it has always worked this way. The uncomfortable part is not that somebody erred. The uncomfortable part is a property nobody chose and nobody discusses. On every crewed flight of this vehicle, forever, the propulsion system destroys itself before anyone can examine it. Let me say that a different way, because it took me a while to absorb. For this one class of problem, engineers do not get to do failure analysis. Not the way engineering has done failure analysis for 150 years. They cannot take the part apart on a bench. They cannot section the valve seat and examine the sealing surface under magnification. They cannot install it in a test rig and reproduce the conditions until it fails again and shows them exactly why. They have telemetry, which is real data and genuinely useful. They have ground units, which are similar to the flight article, but those ground units have already been demonstrated by a factor of 10 to behave differently in the environment that matters. That is what they must design a fix from. Kshatriya was direct about what that fix probably involves. He said he was fairly sure they would need to at minimum tweak the design. Then he said, if not fundamentally change the way the valve works. Fundamentally change the way the valve works. Based on an object that no longer exists in physical form anywhere. Somebody inside that program understood exactly what was coming, and what they chose to do about it during the flight itself is the most quietly impressive decision of the entire mission. Part 10. The deposition. There had been a demonstration scheduled for the middle of the flight. The crew were to hand fly the spacecraft manually and prove out the controls. It was a legitimate objective with real engineering value, and it sat on the timeline. They cancelled it. In its place, they ran the propulsion system through a deliberate sequence of thermal tests. They pointed the entire spacecraft toward the sun and held it there. Then they rotated and pointed it away from the sun and held that. They watched what the leak rate did as the hardware heated and cooled. They recorded everything the gauges reported through every stage of that cycle. Understand what they were not doing, because it changes the meaning entirely. They were not troubleshooting the problem, because they knew they could not fix it. There is no way to reach that hardware in flight, no way to replace a valve seat in vacuum. There was also no operational reason to try. The mission did not need the engine again, and everyone knew it. They were taking evidence. They were extracting every measurement obtainable from a physical object during the final days of its existence. They knew that within a week, that object would be gone permanently. Everything they failed to measure in those hours would remain unmeasurable for the rest of time. That is not a routine engineering test. That is a deposition. Those engineers were taking a statement from a witness scheduled for destruction. They knew the date of the destruction, and they had scheduled it themselves. They asked every question they could think of while the witness was still available to answer. I need you to feel the weight of that, because it is unusual in a way that is easy to skim past. Engineers almost never operate under a hard evidentiary deadline they set themselves. Aircraft investigators recover wreckage months later. Metallurgists examine failed components years after a fracture. Here, the hardware had a scheduled execution date, and everyone involved knew it. So they used the time. They gathered thermal response data across a full solar cycle. They characterized how the leak rate changed as the metal expanded and contracted. And this is where I want to give NASA genuine credit, because that decision was correct. Cancelling a crew demonstration to gather data on a component you cannot fix requires clear thinking. It requires someone to recognize that the information mattered more than the checklist item. Then, on the 10th of April, the module separated at 400,000 feet and burned. So NASA now holds a body of flight telemetry describing the behavior of a component that no longer exists. They will redesign that component from those measurements. They will build a new valve, test it on the ground, and install it in a future service module. And when that new valve flies, it will also burn up over the ocean. That is the loop this program is now inside. And a reasonable person at this point asks a fair question. Is that really so unusual? Engineers work from indirect evidence constantly. Aircraft investigators reconstruct crashes from fragments scattered across mountainsides. Physicians diagnose conditions they will never see directly. That objection is completely fair, and answering it properly requires going backward. Because NASA has been in this situation before, 3 separate times, and each one ended differently. The first involves a tank that fell about the width of 2 fingers. Part 11. The tank that was dropped 2 inches. Take yourself to October of 1968. There is an oxygen tank sitting in a facility, and it carries a serial number. 10,024X. TA0009. It was originally built for the Apollo 10 service module. Then, plans changed, as plans constantly did in that program. Technicians needed to remove the tank and set it aside for later use. During that removal, the tank was dropped. It fell approximately 2 inches. 2 inches, not from a roof and not down a flight of stairs. It shifted and dropped roughly the width of 2 of your fingers. That drop jarred an internal fill line inside the tank. Nothing visible happened at all. There was no dent, no crack, no external sign that would make anyone stop. The tank was inspected afterward and cleared for use. It went back into the flow of hardware and was eventually installed on Apollo 13. Now come forward to the 16th of March, 1970. Apollo 13 is running a countdown demonstration test at the Cape. Part of that test involves filling the cryogenic tanks and then emptying them again. When they attempt to empty tank number 2, it refuses to drain properly. It sits there, stuck at roughly 92% full. The oxygen will not come out the way it should. That is the fill line. That is the damage from 2 inches, 18 months earlier, finally announcing itself. Nobody knew that at the time. What they knew was that they had a tank that would not empty, and a launch schedule. So they devised a workaround. And I want you to notice its shape, because you have already seen this shape once tonight. Rather than pull the tank out and replace it, which would cost weeks, they used the heaters inside the tank. Run the internal heaters, warm the liquid oxygen, let it boil off as gas and vent. It worked exactly as intended, and the tank emptied. But those heaters contained thermostatic switches designed years earlier for a 28-volt spacecraft system. The ground support equipment at the Cape ran at 65 volts instead. Those switches had never been upgraded when the specification changed. Under 65 volts, during those long hours of boiling off oxygen, the thermostats welded themselves shut. The temperature inside that tank climbed far higher than anyone monitoring the process realized. The insulation on the internal wiring was damaged. Apollo 13 launched on the 11th of April, 1970. It carried an oxygen tank containing damaged internal wiring, immersed in liquid oxygen. 55 hours and 55 minutes into the flight, a routine instruction went up. Stir the cryogenic tanks, which was done regularly to keep contents from stratifying. Current flowed through damaged wire inside a pressurized vessel full of oxygen. The tank ruptured. 3 men found themselves 200,000 miles from home in a spacecraft that had just lost most of its ability to sustain them. Now, the parallel to Artemis II is exact in one respect and different in another. What is exact is the process. A known anomaly observed on the ground in a system before flight. A review conducted by competent people. A workaround that solved the immediate operational problem. A formal decision that flight was acceptable. Every one of those steps was made by careful people with defensible reasons. The Courtright Review Board investigated the accident afterward. It did not conclude that anyone had been reckless or negligent. It concluded that the pre-flight drop and gaps in the review process were causal. The system designed to catch this kind of thing did not catch it. Not through laziness, but because each individual step looked reasonable in isolation. What is different, and I want to be honest about it, is severity. Nobody aboard Artemis II was ever endangered by that helium leak. The comparison is not between outcomes at all, it is between decision processes. And there is one more difference, which matters more than either. After Apollo 13, investigators could go and look. They had the flown tank number 1 for comparison. They had identical ground units available for testing. They had wiring specifications and thermostat part numbers and complete test records from the detanking. They reconstructed the failure chain link by link because the physical evidence existed. They found the 2-inch drop from 18 months earlier. They found the voltage mismatch in switches nobody had thought about in years. They found it because they could go and look. Hold that phrase, because the next 2 cases are about what happens when you cannot. And the first of them begins 3 years earlier, on a launch pad with a spacecraft that never left the ground. Part 12. The fire that lasted 17 seconds. The 27th of January, 1967. 3 astronauts are strapped inside an Apollo command module on Launch Complex 34. The rocket beneath them is not fueled. This is a plugs-out test, meaning the spacecraft runs on internal power while still on the pad. It was classified as non-hazardous. That classification is the first thing worth noticing. Gus Grissom commanded the crew. Ed White had been the first American to walk in space. Roger Chaffee was preparing for his first flight. The cabin was pressurized with pure oxygen at slightly above sea level pressure. That is roughly 16.7 pounds per square inch of pure oxygen. In that atmosphere, materials that merely smoulder in ordinary air burn ferociously. The cabin contained a great deal of nylon netting, and Velcro, and paper checklists. Wiring ran beneath the crew couches in bundles that had been repeatedly accessed and modified. A fire started somewhere below Grissom's couch, almost certainly from damaged wiring insulation. In pure oxygen at that pressure, the fire spread through the cabin in seconds. The pressure inside rose so fast that the hull ruptured within about 17 seconds, and the hatch opened inward. That single design decision is the one that haunts the entire history of the program. An inward opening hatch cannot be opened against internal pressure. As the cabin pressure rose, the hatch was pressed more tightly shut by physics itself. It required removing bolts, and the standard egress procedure took roughly 90 seconds under ideal conditions. The crew had nothing close to 90 seconds. Grissom, White and Chaffee died on a launch pad in a spacecraft that was never going to fly that day. The subsequent review board found what these reviews always find. The pure oxygen atmosphere was a known hazard, and it had been accepted. The quantity of flammable material had been noted, and it had been accepted. The hatch design had been debated, and the existing design had been retained. None of those decisions were made by fools. Pure oxygen simplified the life support system enormously and saved weight. The inward hatch was chosen partly because an outward hatch had blown prematurely on a previous flight. Every choice had a rationale. The rationales were individually sound and collectively fatal. Apollo 1 changed everything about how that program handled accepted risk. The atmosphere on the pad was changed to a nitrogen and oxygen mixture. Flammable materials were removed wholesale. And a new hatch was designed that opened outward and could be released in seconds. But here is why this case belongs in this story specifically. Investigators had the spacecraft. They had the burned command module sitting in front of them. They disassembled it over months and photographed every component. They traced wiring bundles and identified the probable ignition region. They tested materials in identical atmospheres and watched them burn. The evidence was blackened and it was terrible to examine, and it existed. 3 catastrophes, and in 2 of them the wreckage told the story. The third is different, and it is the closest parallel to a valve that burns up over the Pacific. Part 13. The wing that burned before anyone could look. The 1st of February 2003. Space Shuttle Columbia broke apart over Texas during re-entry. 7 people died. Rick Husband, William McCool, Michael Anderson, Kalpana Chawla, David Brown, Laurel Clark, and Ilan Ramon. The physical cause is well established now. During launch, 16 days earlier, a piece of insulating foam separated from the external tank. It struck the leading edge of the left wing. That leading edge is built from a material called reinforced carbon-carbon. It is what protects the wing from re-entry heating, and it is not repairable in flight. The impact made a hole in it. On the way home, superheated gas entered through that hole. It destroyed the wing structure from the inside, while the crew were still flying a normal descent. But the physical cause is not why this case matters here. Foam shedding was not new on the 1st of February, 2003. Foam had come off the external tank on 65 of the 79 missions where photography was clear enough to tell. 65 out of 79. That is not an anomaly rate. That is a characteristic. And because it happened almost every time, and because nothing catastrophic had ever resulted, it had been quietly reclassified, not through any formal decision anyone signed. It had stopped being treated as a safety of flight issue and become a maintenance issue. A turnaround nuisance. Something that made the external tank annoying rather than something that could kill a crew. The Columbia Accident Investigation Board delivered its report on the 26th of August 2003. The finding that made that report historic was not about foam at all. The board concluded that the organisational causes were as significant as the physical cause. Schedule pressure. Descent that was muted as it travelled up the management chain. Engineers who requested imagery of the wing while Columbia was still in orbit, whose requests did not survive. A risk normalised so thoroughly that the people carrying it no longer perceived it as risk. Now here is why this case is the closest parallel to Artemis II, and it has nothing to do with foam. The evidence was destroyed on re-entry. The left wing of Columbia, the actual object that failed, does not exist. The reinforced carbon-carbon panel with the hole in it was consumed by the event it caused. Investigators recovered debris across East Texas and Louisiana. Tens of thousands of fragments were catalogued in an extraordinary recovery operation. Volunteers walked search lines for months across hundreds of square miles. But the failure surface itself, the single object you would most want under a microscope, was gone. So consider the problem those investigators faced. They had a probable cause based on launch imagery. They had a theory about foam striking a specific panel at a specific angle. They had no physical evidence of the impact site, because the impact site had been vaporized. They could not prove it by examination, because there was nothing left to examine. What they did instead is one of the more remarkable acts in the history of accident investigation, and it happened in a parking lot in San Antonio with a nitrogen cannon and a piece of a retired spacecraft. Part 14. The Cannon in San Antonio. In July of 2003, investigators gathered at the Southwest Research Institute in San Antonio, Texas. They had built a nitrogen gas cannon capable of firing large objects at precise velocities. They loaded it with a block of external tank foam matched to the piece that had come off Columbia. Then they aimed it at a real space shuttle wing leading edge panel, not a mock-up and not a model. An actual flight-qualified, reinforced carbon-carbon panel, taken from the shuttle inventory. they fired the foam at approximately 500 miles an hour. The foam blew a hole in the panel roughly 16 inches across. 16 inches. In a material engineers had described for years as far too tough to be damaged by something as light as insulating foam. The room reportedly went silent when they saw it. That test ended the argument. Not the recovered debris, and not the launch imagery, and not the computer modelling. A physical reconstruction of an event whose original evidence no longer existed. Now I want you to notice precisely what made that reconstruction possible. Because it is exactly what Artemis II does not have. They had the original hardware design fully documented. They had spare panels available from inventory. They had photographic evidence of the strike captured by launch cameras. They knew the approximate impactor, the approximate velocity, and the approximate angle. They could recreate the conditions because they knew what the conditions were. For the Orion valve, the conditions are the unknown part. Ground behaviour and flight behaviour differ by a factor of 10, and nobody has fully explained why. Something about the flight environment is doing something the ground rig does not reproduce. The thermal cycling of sun and shadow, the vacuum, the vibration history of launch, some combination of those. That is not a case where you know the conditions and need to confirm the outcome. That is a case where the outcome is what you measured, and the conditions are what you are guessing at. Let me put it as directly as I can. Columbia's investigators had to rebuild the crime scene from known inputs. NASA's valve engineers must first work out what the crime scene was. That is a harder problem, and it is a permanently harder problem, because the next service module will also burn up, and the one after that, and every single one afterward for as long as this vehicle carries people. Every future test of the redesigned valve ends the same way. The test article is destroyed before anyone can inspect it. You build the fix, you fly the fix, and the only evidence is telemetry from a machine already falling toward incineration. 16 inches of shattered carbon-carbon settled the Columbia question in an afternoon. There is no equivalent afternoon available here, and there never will be. Which leaves one obvious question hanging. If the evidence always burns, how does an organisation ever notice that something has gone quietly wrong? The answer to that was worked out after a launch on a January morning in 1986, when engineers spent the previous night arguing about the temperature. Part 15. The night they argued about 53 degrees. The 27th of January, 1986. The evening before Challenger flew. Engineers at Morton Thiokol held a teleconference with NASA that night. Thiokol built the solid rocket boosters, and their engineers were worried about the weather. Their concern was the O-rings sealing the joints between booster segments. Those rings are rubber, and rubber stiffens as it gets cold. A stiff seal does not spring back into place quickly enough to seal. The forecast for the morning was far below anything the program had flown in. Roger Boisioli and his colleagues made a recommendation that night. Do not launch below 53 degrees Fahrenheit, which was the coldest previous flight. They were overruled. The recommendation was reversed before the call ended. Challenger launched the following morning at roughly 36 degrees. 73 seconds later, the vehicle broke apart over the Atlantic. Francis Scobie, Michael Smith, Judith Resnick, Ellison Onizuka, Ronald McNair, Gregory Jarvis, Krista McAuliffe. 7 people in front of a national television audience that included school children watching a teacher fly. The Rogers Commission investigated. And on the 11th of February, 1986, Richard Feynman did the thing everyone remembers. He took a sample of O-ring material during a public hearing. He compressed it with a small clamp, dropped it into a glass of ice water, and waited. Then he removed the clamp and showed that the rubber did not spring back. A physicist with a glass of ice water demolished months of institutional argument in under a contribution that matters most is not the ice water. It is the appendix he wrote to the Commission's report, and the sentence closing it. He wrote that for a successful technology, reality must take precedence over public relations. Then he wrote that nature cannot be fooled. Nature cannot be fooled. 9 days in space, and the leak rate is whatever the leak rate is. It does not care what the ground testing predicted, and it does not care what anyone signed. Now I want to be careful drawing this parallel, because Challenger involves something Artemis II did not. There was a specific recommendation not to fly, made by the engineers closest to the hardware, and it was overruled the same night. Nothing remotely like that happened before Artemis II. The helium leak was reviewed and accepted, and the people closest to it agreed with the decision. The free return trajectory made that agreement technically sound. I am not going to tell you NASA overruled its engineers here, because it did not. What Challenger gives us is something more useful than a villain. It gave us a name for the mechanism that kills programs quietly, and that name came from a sociologist rather than an engineer. Part 16. How a deviation becomes a characteristic. Diane Vaughan spent years studying the Challenger decision. What she produced was the single most useful concept in this entire field. She called it normalization of deviance. Here is what it means in practice. You observe something that is not supposed to happen. Foam comes off a tank. An O-ring erodes. A valve leaks a little helium. It sits outside the design intent. By definition, it is a deviation. But nothing bad happens. So you fly again, and it happens again, and again nothing bad happens. And slowly, without anyone making a conscious decision, the deviation stops being a deviation. It becomes a characteristic. It becomes simply how this hardware behaves. The paperwork may still call it an anomaly. The institution has stopped feeling it as one. Notice how perverse the driving mechanism is here. This process runs on success, not on failure. Every flight where nothing goes wrong makes the next acceptance easier to sign. A safety record does not only measure risk, it also quietly erodes your perception of the risk you are carrying. Think of it like a smoke alarm that chirps occasionally for no reason. The first time you investigate immediately. The 10th time you note it and continue with your evening. The alarm has not changed at all. Your relationship to the sound has changed completely. Now let me apply that honestly to Artemis II. I want to do this fairly rather than dramatically. A helium leak was observed on Artemis I in 2022. Nothing bad happened. The same leak was present before Artemis II. It was reviewed, it was accepted, and nothing bad happened. That is 2 data points. 2 is not a pattern, and I am not going to pretend otherwise. 2 is nowhere near the 65 foam events out of 79 that preceded Columbia. It is nowhere near the years of eroded O-rings that preceded Challenger. There is also a genuine technical distinction protecting this case. That leak was never in a safety-critical path on the missions where it was accepted. The free return trajectory meant propulsion was not load-bearing for crew survival. That is a real argument, not an excuse, and it deserves to be stated clearly. So I will not stand here and tell you NASA has normalized deviance on Orion. The evidence does not support that claim, and inventing it would be dishonest. But I will tell you what does concern me, and it is structural rather than cultural. The mechanism Vaughan described requires 2 ingredients working together, a recurring anomaly and an inability or unwillingness to fully investigate it. The first ingredient is present. That leak has now appeared on both flights of this vehicle, and the second ingredient is not about willingness at all. Nobody is blocking the investigation. Nobody is protecting a schedule by suppressing dissent. They cannot fully investigate it, because the hardware is gone every single time. Let me say that again, because it is the whole point. In every historical case tonight, the institution's failure was a choice. Choices are correctable. You can build better descent channels, and NASA did after Columbia. You can change a hatch design, and NASA did after Apollo 1. You can give an engineer the standing to stop a launch, and Kamada's open letter worked in exactly that tradition. Here the constraint is not cultural. You can fix a culture through leadership and process. You cannot fix an architecture without redesigning the spacecraft. And before anyone concludes this is a uniquely American problem or a uniquely NASA problem, there is a nearly identical case. It happened on a different spacecraft, built by a different company, and it produced an image I have not been able to shake. Part 17. The seal the size of a shirt button. In June of 2024, Boeing's Starliner carried 2 astronauts to the International Space Station. It was the vehicle's first crewed test flight. It developed helium leaks in its propulsion system. Steve Stitch ran NASA's Commercial Crew program at the time. In May of that year, he described the source, and the description has stayed with me. He said it was a seal, a rubber ring about the size of a shirt button. He said it had the thickness of about 10 sheets of paper. It sat in the flange feeding one of the thrusters. A shirt button. 10 sheets of paper. That is the component standing between a pressurized propulsion system and vacuum. Stitch also said at the time that a leak 100 times worse would still allow Starliner to fly safely. He was making a point about margin, and he was not being reckless in saying it. Now remember the woven basket from earlier. Remember gravel and sand and water. That shirt button seal would hold nitrogen indefinitely. It would hold almost any gas you asked it to hold. It could not hold helium, because helium is the water. So where does the comparison to Orion hold? It holds completely on the physics. Seals and valve seats are the weak point of every pressure-fed propulsion system ever built. This is not incompetence at Boeing or incompetence at Airbus. It also holds on access, which is the point that matters here. Starliner's service module is also expendable, and it also burns up on the way home. Those seals and thrusters were destroyed before anyone could examine them on a bench. 2 spacecraft, 2 continents, 2 manufacturers, the same class of problem in the same class of system. And both of them destroyed the evidence on the way home. Where does the comparison break down? It breaks down badly on severity, and I want to be precise about that. Starliner's problems cascaded in a way Orion's did not. The helium leaks were accompanied by thruster failures during the approach to the space station. The situation became serious enough that NASA made an extraordinary decision. Those 2 astronauts did not come home on the vehicle that carried them up. They returned on a SpaceX Dragon after a stay that ran vastly longer than planned. Nothing remotely like that happened on Artemis II. The Orion crew was never at risk, and the vehicle completed its mission. The leak was a data point, not an emergency. So when you see a straight line drawn between Starliner and Orion, be skeptical. The claim that Artemis II nearly went wrong is not supported by anything. The honest comparison is narrower and I think considerably more interesting. This is not a company problem at all. It is a design philosophy shared across the entire industry, and almost nobody discusses it. And if you want proof that it runs deeper than spacecraft, look at the rocket underneath. Part 18. The rocket that also needed new valves. The Space Launch System is the largest rocket NASA has flown since the Saturn V. It is the vehicle that threw Orion at the Moon. It also needed helium valves replaced before both Artemis launches. Sit with that for a second, because it reframes everything, not the spacecraft, the rocket. A completely separate vehicle, built by different contractors, using different hardware, same element. Same class of component, same problem. During the Artemis I launch campaign in 2022, hydrogen leaks and valve issues caused repeated scrubs. The countdown was halted more than once by problems in this general family. Engineers replaced seals and worked the issue for weeks. SpaceX has scrubbed launches over valve problems of its own. Every operator flying pressure-fed systems has a version of this story. So here is the pattern across the industry, stated plainly. Everyone uses helium because it is the only sensible choice. Everyone struggles to contain helium because it is the hardest gas to contain. Everyone builds expendable modules because carrying dead mass home is wasteful. And therefore, everyone destroys their propulsion evidence on every single flight. Nobody chose that outcome. It emerged from 3 separate decisions, each of which is correct in isolation. That is what makes it interesting rather than scandalous. There is no villain here and no cover-up to expose. There is an industry-wide blind spot produced by 3 good decisions interacting. Now, is there a way around it? There are partial answers, and they deserve mention. Reusable spacecraft change this equation entirely. A vehicle that returns its propulsion system to the ground can be inspected between flights. That is one of the genuinely underappreciated advantages of reusable design, and it has nothing to do with cost. You do not only save money by flying hardware twice, you get to examine hardware that has flown. Orion is not that kind of vehicle, and it was never designed to be. The crew module is partially reusable, and NASA plans to refly some capsule components. The service module never comes home. There is one more possibility, and it is the direction the industry is quietly moving. Instrument the module more heavily so telemetry substitutes for inspection. More sensors, more channels, more data captured before destruction. That is essentially what the Artemis II crew did manually with those thermal tests. But sensors tell you what happened. They do not tell you why it happened at the level of a sealing surface. You cannot photograph a microscopic scratch with a pressure transducer. Which brings the story back to a specific calendar and a specific engine burn at a specific moment in the near future. Because the redesign has a deadline, and it is closer than most people realize. Part 19. The mission that stopped being a landing. Kshatriya drew the line more clearly than anyone. He said he does not need those valves to hold pressure in the same way for a mission orbiting in low Earth orbit. Then he said that for a lunar orbit mission, he does. That single sentence contains the entire schedule, and to understand it, you need to know what Artemis III actually is now. It changed, and a great many people have not caught up. On the 27th of February this year, NASA reprofiled Artemis III. It is no longer the lunar landing mission. It is now a crewed test flight in low Earth orbit. At an altitude of roughly 460 kilometers, Orion will rendezvous and dock with commercial lunar lander hardware there. Both SpaceX and Blue Origin are expected to provide test articles. It is targeted for late 2027. The crew was announced on the 9th of June this year. NASA drew a comparison to Apollo 9, and the comparison is fair. In March of 1969, Apollo 9 tested the lunar module in Earth orbit. Nobody went near the moon on that flight. The logic is identical. Prove the hardware where home is 90 minutes away rather than 3 days. Which means Artemis III does not need those valves fixed. The propulsion demands are modest, and the abort options are excellent. The first crewed landing has moved to Artemis IV in 2028. That is a lunar mission, and the difference is not administrative. It requires the main engine to perform lunar orbit insertion. Let me explain what that burn actually is, because it is the moment everything hinges on. You arrive at the moon carrying enormous velocity. If you do nothing, you swing past and come home, which is the free return. To enter lunar orbit, you must slow down enough to be captured by the moon's gravity. That means firing the main engine at full performance for a sustained period. There is no gentle version of that burn. It either happens correctly or you do not enter orbit. And a sustained main engine burn is exactly what requires the helium system to hold full pressure. Every small thruster firing on Artemis II avoided that demand entirely. So the redesigned valve must be finished, qualified, and installed in a service module built in Bremen. It must be ready for a 2028 flight. How much will that redesign cost? And when will it be complete? As of today, there is no public cost figure and no firm public schedule. That is not a gap in my research. That is the state of the public record. A component NASA's own associate administrator has called a probable extensive redesign, on the critical path to the first moon landing in more than 50 years, with no published price and no published date. And that redesign is not the only clock running towards 2028. There is a second one, and it is running late. Part 20. 2 clocks running toward the same year. In March of this year, NASA's Office of Inspector General published its report on the Human Landing System contracts. The numbers deserve to be heard precisely. Since the program began in 2019, NASA has obligated $6.9 billion for lander development. The agency estimates spending $18.3 billion through fiscal year 2030. The same report found SpaceX more than a year behind on 3 critical milestones. Its critical design review, its propellant transfer demonstration, its uncrewed lunar landing. That middle item deserves attention because it is the least understood and the most important. Starship cannot reach the moon on a single launch of fuel. The architecture requires transferring propellant from one Starship to another in orbit. Nobody has ever done that with cryogenic propellant at scale. It is the single most unproven capability in the entire Artemis plan. That demonstration was scheduled no earlier than late this year. The uncrewed lunar landing sits around the middle of next year. Blue Origin faced its own difficulties with the Blue Moon Mark II lander. The company was still resolving mass and propulsion shortfalls. Nearly half the action items from its 2024 preliminary design review remained open a year later. In February of this year, the Aerospace Safety Advisory Panel issued a warning. That panel is chaired by retired Lieutenant General Susan Helms, herself a former astronaut. The panel warned that the Artemis III landing plan as configured carried too much risk. That warning came weeks before NASA restructured the mission. Notice the sequence there, because it is a system working correctly. An independent safety body raised an objection, and the program changed. Then, on the 23rd of July this year, the Government Accountability Office published its annual assessment. It contained a finding I have not been able to stop thinking about. The Orion crew capsule accounts for over half of the major project's annual cost overruns. It accounts for almost 75% of their cumulative cost overruns. The portfolio's cumulative overrun had risen from $4.4 billion to nearly $4.7 billion. Almost 3/4 of cumulative overruns across NASA's entire major project portfolio. Concentrated in this one spacecraft, and all of this is happening against a budget picture that shapes everything. The fiscal year 2027 request was released on the 3rd of April this year. It proposed cutting NASA from $24.4 billion to $18.8 billion. That is a 23% reduction to the agency overall. The Science Mission Directorate would fall by roughly 47%, from $7.3 billion down to $3.9 billion. But exploration went up, from $7.8 billion to $8.5 billion, an increase of $731 million. The stated purpose of that increase was to land astronauts on the Moon by 2028. Administrator Isaacman was asked on the 5th of April whether he supported the cuts. He said yes, of course he did. So look at the shape of what is converging on a single year. A propulsion component with no published fixed schedule, landers running more than a year late on unproven capabilities, a spacecraft responsible for 3/4 of the portfolio's cumulative overruns. Science funding cut nearly in half while exploration is funded upward and given a hard date. The hard date concerns me more than any other item on that list, and to explain why, I have to describe two futures that both start from exactly here. Part 21. The branch nobody can test. Let me lay out both branches honestly, and tell you which one the evidence favours. The first branch is ordinary, and I think it is considerably more likely. Airbus and NASA redesigned the valve system successfully. They used the flight telemetry from those repurposed test hours aboard Artemis II. They build new ground rigs that better replicate the flight thermal environment. They know now, by a factor of 10, that the old rigs were not adequate. That knowledge alone is worth a great deal. They qualify a new valve, install it in the service module for Artemis IV, and it flies in 2028. Lunar orbit insertion happens exactly on schedule. Nothing about this ever becomes a story again, except in accounts like this one. If I had to bet, I would bet on that branch. These are extremely capable engineers who identified this problem themselves. They disclosed it publicly without being forced to, which is not nothing. The second branch is not catastrophe. It is subtler, and it is the one holding my attention. In the second branch, the redesign runs into the wall that created the problem. They build a new valve and test it thoroughly on the ground. It performs beautifully on the ground. So did the old one. And they have no way to know whether it behaves differently in flight until it flies. When it flies, it burns up. So Artemis IV launches with a valve everyone believes is fixed. That belief rests on ground testing, which has already been demonstrated, once, to be wrong by an order of magnitude about this exact component. If the new valve also leaks worse in flight, they will learn it from telemetry. They will learn it on a mission that actually needs the engine. They will learn it near the moment of lunar orbit insertion. That is not a prediction of disaster, and I want that understood clearly. The margins are large, abort modes exist, and free return options remain available. It is a description of an epistemic situation, not a physical one. They will fly a fix they cannot fully validate into the first mission where the fix matters, and the validation data will destroy itself on the way home. Which brings me to the thing that actually unsettles me, and it is not the helium. The helium leak is a small problem. It never threatened anyone, and it will probably be engineered away by competent people. The real danger is the blind spot the leak revealed. For 2 years, an enormous quantity of attention was directed at the heat shield. An Inspector General report. An independent review team. A materials investigation running roughly 2 years. Former astronauts writing open letters. A new administrator sitting through a half-day review and putting his name on the determination. All of that machinery worked correctly, and it produced the right answer. The shield was fine, and while every eye in the program was on the visible risk, the invisible one sat in the plumbing, already known, already documented on the previous flight, quietly signed off, because on that particular mission profile it genuinely did not matter. That is not a failure of competence, that is a property of attention itself. Attention is finite, scrutiny concentrates, and the risk that gets normalized is never the one everybody is arguing about. It is always the one that seemed too minor to argue about. The heat shield received 2 years of adversarial review because people were frightened of it. The valve received a low leak rate, an acceptable rating, and a launch. And there is one final layer underneath that, which is the part I keep returning to. If the heat shield had failed, we would have known immediately and completely. The capsule comes home. The evidence comes home. Divers photograph it in the water before it is even lifted. That system is observable. The propulsion system is not. It reports its condition, and then it destroys itself. Part 22. Apollo burned its evidence too. There is a detail about Apollo that almost nobody mentions, and it changes how you read this entire story. Apollo used the same architecture, a command module that came home and a service module that did not. The Apollo service module carried the fuel cells and the oxygen tanks. It carried the main engine that got the crew out of lunar orbit. It carried the electrical power and the consumables and the propellant, and on every single Apollo flight, it was jettisoned before re-entry and destroyed. 11 crewed Apollo missions flew. 11 service modules burned in the atmosphere over the Pacific. So when engineers wanted to understand how those systems had behaved in flight, they had telemetry. They had crew reports. They had ground units built alongside the flight articles. They did not have the hardware. Now hold that against Apollo 13, because it produces one of the strangest images in the history of spaceflight. After the oxygen tank ruptured, the crew stayed attached to the crippled service module for days. They used the lunar module as a lifeboat, and they kept the damaged section with them. Only shortly before re-entry did they jettison it, and as it drifted away, they photographed it. Those photographs are extraordinary. An entire panel of the service module is simply gone, blown outward, the interior structure exposed and torn. Jim Lovell described seeing it and understanding immediately how serious the damage had been. So they had photographs. They had a visual record of the outside of the failure. They did not have the tank. That tank was inside the section that burned, and it burned exactly as every other service module had burned. The single component that had failed, the object that had nearly killed 3 men, was destroyed within hours of being photographed. And the investigation still succeeded. I want to be careful here, because this cuts against the argument I have been building, and I would rather show you the strongest version of the counter case than hide it. The Courtright board reconstructed that failure without the tank. They used the ground twin. They used the detanking records from the 16th of March. They used the wiring specifications and the thermostat part numbers. They ran tests on identical hardware until they reproduced the conditions and watched the failure happen. So it can be done. The historical record proves it can be done on a component that no longer existed more than 50 years ago. But notice what made it possible, because this is the whole distinction. They knew what the conditions had been. They had the detanking log. They knew the voltage. They knew the duration. They knew the temperature the switches had been exposed to. They were not guessing at the environment. They were reproducing a documented one. The Orion valve is the opposite situation. The environment is the unknown quantity. Ground behavior and flight behavior differ by a factor of 10, and nobody has explained the gap. You cannot reproduce a condition you have not identified. Apollo 13's investigators had a mystery about a component. NASA now has a mystery about an environment. Those are not the same kind of problem, and the second one is harder, and there is a second anomaly from Artemis II that almost nobody reported, which tells you something about how much of this flight is still unresolved. Part 23. The second thing that broke. The helium leak was not the only anomaly aboard Artemis II. The waste management system malfunctioned. In plain language, the toilet failed, and it failed at least twice. I understand that sounds trivial. It is not, and I want to explain why it matters more than it appears. Every closed-loop life support system on a spacecraft handles waste through a vent line. That line carries material overboard into vacuum through a controlled path. On a mission lasting 9 days with 4 people, that system runs continuously. It is not optional, and there is no manual alternative that works well. The problem on Artemis II was traced toward the vent line, and as of the most recent public reporting, the root cause investigation was still open. Still open. Months after splashdown, NASA has said corrective action will be applied before Artemis III flies. That is the correct response, and I have no criticism of it. But look at the shape of this, because it is the same shape as everything else in this story. A system that is not glamorous, a system nobody writes headlines about, a system that failed in flight in hardware that is partly in the module that burns, and an investigation that is still running because the physical evidence is limited. Now here is why I raise it at all. 2 anomalies is a different statistical picture than 1. If the only problem on Artemis II had been the helium valve, you could reasonably call it an isolated component issue. Hardware has flaws. That is normal. 2 independent systems behaving unexpectedly on a 9-day flight is a different conversation. It suggests the ground testing regime across multiple subsystems is not fully capturing flight conditions, and that is the concerning version of this story. Not that one valve leaked, that the process which certified one valve as flight-worthy also certified everything else. Consider what a 9-day mission actually tests. Artemis III is planned as a longer flight in low Earth orbit. Artemis IV goes to lunar orbit and stays. Every additional day is another day of thermal cycling on hardware that has now demonstrated, twice, that it behaves differently in space than on the ground. I am not predicting a failure on a longer mission. The margins are real, and the abort options are real. I am pointing out that 9 days is a short exposure, and the 2 anomalies we know about both emerged inside that short exposure. What emerges at 30 days, or at 60, in hardware nobody has flown that long? Nobody knows, and there is no way to find out except by flying it. Which brings us to the vehicle that carried all of this to the pad, and to a cost figure that has never been fully explained. Part 24. The rocket nobody can afford to cancel. The Space Launch System has a history that explains a great deal about the pressures in this story. Its origins run back to the Constellation program, announced in 2005. Constellation was cancelled in 2010. But the hardware and the contracts did not disappear. They were reorganized into a new rocket, and Congress wrote the requirements directly into law. The Space Launch System was legislated into existence. That is unusual, and it matters. It uses shuttle-derived main engines. It uses shuttle-derived solid rocket boosters. Those choices were made partly for engineering reasons, and partly to preserve an existing industrial base. The first flight was originally targeted for 2017. Artemis I flew in November of 2022, 5 years late on the first flight of a vehicle built from proven components. Now the money. NASA's Office of Inspector General reported that by the then-planned Artemis II launch date, the agency would have spent more than $55 billion across the Space Launch System, Orion, and the ground systems. $55 billion. Let me put that in a frame you can hold. The entire Apollo program, from 1960 to 1973, cost roughly $25 billion in the money of the time. Adjusted forward, estimates place it somewhere near $280 billion in modern terms. So, Artemis is not more expensive than Apollo overall. But Apollo produced 11 crewed flights and 6 landings for its money. Artemis, at $55 billion, had produced 1 uncrewed flight and 1 crewed lunar flyby. and the Inspector General has separately estimated the cost of a single Space Launch System launch at over $4 billion. $4 billion per flight for a vehicle that is entirely expendable. The rocket is destroyed on every mission. The service module is destroyed on every mission. Notice how that compounds with everything else in this story. The economics and the evidence problem come from the same root. An expendable architecture means you throw away the hardware. Throwing away the hardware means you cannot inspect it. And building a new one each time means the cost never falls. The Government Accountability Office put a finer point on it in July of this year. Orion accounts for over half the annual cost overruns across NASA's major projects, and almost 75% of the cumulative overruns. The portfolio's cumulative overrun stood at nearly $4.7 billion. So when you ask why a valve redesign has no published schedule and no published cost, part of the answer is structural. This is a program where cost and schedule reporting has been a persistent problem for 15 years, and it is a program that cannot easily be cancelled because it is written into law and distributed across enough congressional districts to make cancellation politically expensive. That is not a conspiracy. It is how large public engineering programs work everywhere in the world. But it does mean that when a schedule tightens, the pressure has nowhere to go except into technical margin, and there is one case in aviation history where investigators refused to let that happen, at extraordinary expense. Part 25. The wreckage they raised from the ocean floor. On the 17th of July, 1996, TWA Flight 800 exploded shortly after taking off from New York. All 230 people aboard were killed. The aircraft came apart over the Atlantic and fell into the water off Long Island. What happened next is the most complete counterexample to everything I have described tonight. Investigators did not accept that the evidence was gone. They mounted one of the largest wreckage recovery operations ever attempted. Divers, trawlers, and remotely operated vehicles worked the seafloor for months. They recovered more than 95% of the aircraft. Then they took those fragments to a hangar in Calverton, New York, and they rebuilt the aeroplane. Not a model, not a simulation. They constructed a steel frame and hung the recovered pieces on it in their original positions, reassembling roughly 93 feet of the fuselage. That reconstruction took years and cost tens of millions of dollars. And it worked. The reconstruction showed the center wing fuel tank had exploded. Investigators concluded that flammable vapor in a nearly empty tank had been ignited, most probably by a short circuit in the wiring. The finding changed aviation permanently. Fuel tank inerting systems were mandated. Wiring inspection standards were rewritten. Now hold that against the Orion valve, because the contrast is total. TWA 800's evidence was at the bottom of the ocean, scattered across a wide debris field, corroding in salt water. It was recoverable. Expensive, slow and difficult, but physically possible. The service module's evidence is not at the bottom of anything. It is not corroding somewhere waiting to be found. It was converted into vapor and dispersed at high altitude. There is no debris field. There is no salvage operation that could ever be mounted, at any budget, by any nation. That is the distinction I keep returning to. Every other investigation in this story had a physical object, or the possibility of obtaining one. Apollo 1 had the burned capsule. Apollo 13 had the ground twin and the detanking records. Columbia had 38,000 kilograms of recovered debris and spare wing panels to shoot at. TWA 800 had 95% of an aeroplane raised from the sea. The Orion valve has telemetry. And I want to be fair about telemetry, because it is not nothing. Modern flight data is dense and precise, and the engineers reading it are extremely good. But every one of those historical investigations had telemetry too. And every one of them went and got the hardware anyway. They did that because engineers do not trust data about an object as much as they trust the object. That instinct is 150 years old, and it exists for good reason. And there is one program that decided the instinct was worth designing the entire vehicle around. Part 26. The spacecraft that comes home whole. There is a way to solve this problem, and part of the industry has already chosen it. You bring the propulsion system back. A reusable spacecraft returns its hardware to the ground. Engineers can then inspect the components that flew on a bench with instruments at leisure. That capability is discussed almost entirely in terms of cost. Flying hardware twice is cheaper than building it twice, but the inspection benefit may matter more than the money, and it is barely mentioned. Consider what a reusable vehicle gives you after every flight. Seals that have experienced vacuum, valves that have gone through real thermal cycling, surfaces that have seen actual re-entry. You can section them. You can measure wear. You can compare the same component across 10 flights and watch how it degrades. That is a dataset nobody flying expendable hardware will ever have. Orion is partly reusable. NASA has said it plans to refly certain crew module components on later missions, and some avionics from Artemis I were reused on Artemis II. That is real, and it is worth acknowledging. But the crew module is the part that was never the problem. The service module is the part with the valve, and the service module is expendable by design. There is no version of the current Orion architecture where that changes. So the question becomes whether you could instrument your way out of it. More sensors, more channels, higher sampling rates. Capture so much data before destruction that you no longer need the object. That is essentially what the Artemis II crew did by hand when they cancelled the piloting demonstration and ran those thermal tests. And it is a reasonable direction. Flight instrumentation has improved enormously and will keep improving. But there is a hard limit, and it is worth stating precisely. A sensor tells you what a system did. It does not tell you why, at the scale where the answer lives. A helium leak past a valve seat is a microscopic phenomenon. It happens across a sealing surface measured in fractions of a millimetre. The cause might be a machining scratch. It might be a particle of contamination trapped during assembly. It might be a material that lost elasticity at a temperature nobody tested for. Every one of those causes produces the same reading on a pressure sensor, a number that is higher than it should be. You cannot photograph a scratch with a pressure transducer. You cannot identify a trapped particle from a flow rate. To distinguish between those causes, you need the surface under magnification. You need the object. Which means the instrumentation answer has a ceiling, and NASA is already near it, and that limitation is about to meet a deadline that will not move. Part 27. The 20-year-old spacecraft that has flown twice. I want to close this section by putting Orion itself in perspective, because the timeline is genuinely difficult to absorb. Orion was announced in 2005 as part of the Constellation program. 21 years ago. In those 21 years it has flown 3 times. Once on a brief uncrewed orbital test in 2014. Once around the Moon uncrewed in 2022. Once around the Moon with a crew in April of this year. 3 flights in 21 years. One of them with people aboard. Now compare that to the program everyone measures it against. The Apollo Command Module design work began in earnest in 1961. The first crewed flight, Apollo 7, launched in October of 1968. 7 years from start to crewed flight, then 11 crewed missions in 4.5 years. I am not making the lazy argument that the 1960s were better. They were not. Apollo 1 killed 3 men on a launch pad because that program moved fast and accepted risks that would be unthinkable now. The modern program is far more careful, and the carefulness is why 4 people came home in April. But there is a genuine cost to a 21-year development cycle, and it is not only money, it is institutional memory. The engineers who designed the original Orion propulsion architecture are not, for the most part, the engineers working on it now. People retire, contractors change. Design decisions get documented, but the reasoning behind them often does not. When you must redesign a valve 21 years after the architecture was set, you are frequently working from drawings rather than from the person who drew them. And this connects directly to something we saw in the Apollo 13 story. The thermostatic switches in that oxygen tank were specified for 28 volts. The ground equipment ran at 65. Nobody caught it because the specification had been written years earlier by people who had moved on, and the change to the ground equipment had happened somewhere else in the organisation. That is not carelessness. That is what happens to knowledge across long timescales in large institutions. Artemis IV is scheduled for 2028. That would be 23 years after Orion was announced. The valve redesign must be completed, qualified and integrated inside that window by an organisation that has already demonstrated it takes years to resolve a heat shield question, and the redesign has no published schedule and no published cost. So we arrive at the situation this entire film has been building toward: a component that must be fixed, a deadline that will not move, an evidence base that destroys itself, and an institution operating at the far end of a 21-year memory. Part 28. The chemistry that would kill you on the ground. I have described the propellants aboard Orion as hypergolic, and I have told you they ignite on contact. What I have not told you is what those chemicals actually are. The fuel is monomethylhydrazine. The oxidizer is nitrogen tetroxide. Both of them are among the most dangerous substances routinely handled by human beings. Monomethylhydrazine is a clear liquid that smells faintly of ammonia. It is highly toxic, it is absorbed through skin, and it is a suspected carcinogen. Exposure attacks the nervous system and the liver. Nitrogen tetroxide is worse in a different way. It is a reddish-brown liquid that gives off an acrid vapour. Inhaling it damages lung tissue, and the injury can develop hours after exposure, long after a person believes they are fine. Technicians who load these propellants wear fully enclosed suits with their own air supply. The garments look like something from a biological containment facility, because functionally that is what they are. Now, hold that image, because it explains something important about testing. You cannot casually run a fully loaded propulsion system on a bench to see how a valve behaves. Every test involving live propellant requires containment, remote operation, evacuation zones, and a disposal plan. It is slow, it is expensive, and it carries real risk to the people conducting it. So a great deal of valve testing is done with substitutes. Inert gases. Simulant fluids chosen to behave similarly without killing anyone. And that is entirely reasonable. It is how the industry works and there is no alternative. But notice what it means. The ground test may not merely differ from flight in temperature and vacuum. It may differ in what is flowing through the hardware. A seal exposed to nitrogen tetroxide for weeks is not in the same condition as a seal exposed to a harmless simulant for an afternoon. Oxidizers attack materials. Elastomers swell, harden, and lose elasticity, and the leak on Artemis II was on the oxidizer side. I want to be careful because I have not seen NASA state that propellant exposure caused the discrepancy. That is not a claim I can make, and I am not making it. What I can say is that the oxidizer side is the harsher environment, that the leak was found there, and that the flight rate was 10 times the ground rate. Whether those facts are connected is precisely the kind of question you would answer by examining the valve. Which you cannot do. There is one more consequence of this chemistry. and it explains why the leak was described as internal rather than to space. Helium leaking past a valve seat inside a system full of nitrogen tetroxide does not produce a visible plume. It produces a pressure reading that drifts. The most dangerous chemistry in the vehicle produced the quietest possible symptom, and the module containing it was assembled 6,000 kilometers from the launch site in a country that does not fly its own astronauts. Part 29. The Hall in Bremen. I want to take you to northern Germany because the politics of this module matter as much as the engineering. The European Service Module is built by Airbus in Bremen. The program is led by the European Space Agency. 20 main contractors and more than 100 suppliers across 13 countries feed that assembly hall. Here is what that means in practice. The United States cannot fly Orion without Europe. That is not an exaggeration or a rhetorical flourish. The crew module has no propulsion of its own worth the name. No service module, no lunar mission. This arrangement exists because of a trade. Europe supplies the service modules, and in exchange European astronauts fly on Artemis missions and receive allocations aboard the planned lunar station. It is a barter arrangement rather than a straightforward purchase, and it has been in place for over a decade. Now consider what that does to a redesign. A valve modification is not a decision one organisation makes. It involves NASA, which flies the vehicle. It involves the European Space Agency, which leads the module. It involves Airbus, which builds it. And it involves whichever supplier in whichever of those 13 countries actually manufactures the valve. Each of those organisations has its own review process, its own qualification standards, and its own funding cycle. I am not suggesting anyone is obstructive. International collaboration on this scale is genuinely impressive, and it works. But it is slower than a single organisation making a single decision. Every interface between institutions adds time, and the schedule for Artemis IV does not care about that. There is a second consequence, and it is about knowledge. The people who understand that valve most deeply are in Europe. The people who fly the vehicle and read the telemetry are in Houston. The flight data lives on one continent, the design expertise lives on another. That gap is bridged constantly and professionally by people who do this for a living. But recall what we established about Apollo 13. The thermostat specification failure happened because a change in one part of an organisation did not propagate to another part. That was inside a single agency, in a single country, in a program moving at maximum speed. Now distribute the same problem across 13 countries, 100 suppliers, 2 space agencies, and a 21-year development timeline. I want to be clear that no failure of that kind has been reported here. I am describing a structural risk, not an accusation. But structural risk is what this entire story is about. Nobody chose the blind spot. It emerged from the shape of the organisation and the shape of the vehicle. And in 2028, that distributed organisation has to deliver a valve that works during the single most demanding burn of the entire programme. Part 30. The burn that cannot be aborted halfway. I want to describe lunar orbit insertion properly, because everything in this story converges on it. Here is the situation. Your spacecraft has travelled roughly 4 days from Earth and is approaching the Moon at high speed. If you do nothing, you fly past. On a free return trajectory, the Moon's gravity bends your path and sends you home. That is the safe default, and it is what Artemis II did. To enter lunar orbit, you must destroy velocity. You turn the spacecraft so the main engine faces your direction of travel, and you burn. That burn typically runs for several minutes. It requires the propulsion system to deliver sustained full performance, with the pressurization system holding the propellant tanks at working pressure for the entire duration. This is where the helium matters. Every second of that burn, helium is pushing propellant toward the engine. If pressure falls, the flow rate falls, and the engine underperforms. Now consider the geometry, because it is unforgiving. Burn too little, and you do not enter orbit. You continue past the moon on some trajectory that may or may not bring you home. Burn too much, and your orbit is wrong in a different way, and the burn happens, on many profiles, while the spacecraft is behind the moon. Out of direct radio contact with Earth. Let me put that plainly. During the most demanding propulsion event of the mission, nobody on Earth can talk to the crew. Mission Control watches the spacecraft disappear behind the lunar limb, waits, and finds out whether the burn worked when the signal comes back at the predicted time or does not. That is exactly how Apollo did it, and the silence during those passes is one of the most documented sources of tension in the entire program. So the valve that leaked 10 times worse than predicted, in a module that burns up, redesigned from telemetry, must perform correctly during a multi-minute burn behind the moon, with no communication, on a mission carrying 4 people. There are abort options. I want to be fair about that. Mission planners design free return windows and alternate trajectories precisely so that a failed insertion burn is survivable. Apollo 13 is the proof. Their insertion never happened, and they came home on the free return the trajectory designers had preserved. But an abort is not a success. An abort means a mission that cost billions of dollars and years of preparation returns without doing what it went to do. And here is the part that should hold your attention. If the redesigned valve underperforms during that burn, engineers will learn about it from telemetry in real time from a spacecraft behind the moon. Then that service module will come home, separate at 400,000 feet, and burn. The evidence from the failure of the fix will be destroyed exactly as the evidence from the original problem was destroyed. That is the loop. That is why this is not a story about one valve, and there is one institution whose entire job is to see that loop coming and say so out loud. Part 31. The panel whose only power is to say no. The Aerospace Safety Advisory Panel was created by Congress in 1968. It was established in the direct aftermath of the Apollo 1 fire. 3 men died on a launch pad in January of 1967, and one of the consequences was a permanent independent body whose sole function is to look at NASA's human spaceflight programs and report on safety. The panel has no authority to stop a launch. It cannot order a redesign. It cannot withhold funding. Its only power is to publish what it thinks. That sounds weak. In practice it is not, and the reason is that the panel's warnings become part of the public record. An agency that flies against a documented warning has to explain itself afterward. The panel is currently chaired by retired Lieutenant General Susan Helms. Helms is a former astronaut. She flew on the shuttle and lived aboard the International Space Station, and she holds a share of the record for the longest spacewalk ever performed. She is not an outside critic with no standing. She is personally depended on the system she now reviews. In February of this year, that panel warned that the Artemis III landing plan as configured carried too much risk. Weeks later, NASA restructured Artemis III from a lunar landing into a low Earth orbit test flight. I want to be careful about causation. I cannot tell you the panel's warning caused the restructure, and NASA has cited the readiness of the landing systems as the driver. But the sequence is on the record, and the sequence is what a functioning safety system looks like. An independent body identified an unacceptable risk. It published. The program changed. Now hold that against the helium valve, because the comparison is uncomfortable in a specific way. The panel can review a mission plan because a mission plan exists on paper and can be examined by anyone with clearance and expertise. The panel cannot examine a valve that no longer exists. Oversight, at every level, ultimately depends on the ability to inspect something. An Inspector General can audit records, a safety panel can review plans, an accident board can examine wreckage. Every one of those mechanisms assumes an object or a document to look at. The architecture we have been discussing removes the object from that chain permanently, on every flight, by design. So the oversight machinery built after Apollo 1, refined after Challenger, and rebuilt again after Columbia, arrives at this particular problem and finds there is nothing physical left to oversee. That is not a failure of the machinery. The machinery is working exactly as designed, and it caught the Artemis III landing risk. It simply cannot reach this one, and the schedule it is overseeing is now measured against a date that a budget document has already fixed in place. Part 32. The station waiting in orbit around the Moon. There is one more piece of this program that almost nobody outside the field discusses, and it changes the stakes of the valve question considerably. Artemis is not designed to end with a landing. It is designed to build a permanent presence, and the centerpiece of that is a small station in orbit around the Moon. The plan is for Orion to fly out, dock with that station, and serve as the crew's ride home. Now think about what that does to mission duration. Artemis II lasted 9 days. A mission that delivers a crew to a lunar station and later brings them home involves the spacecraft spending far longer in that environment. And here is the specific problem. A docked spacecraft is not doing nothing. It is sitting in sunlight and shadow, cycling thermally for the entire duration of the stay. Every hour of that is another hour of the exact conditions that appear to make this valve behave differently than it does on the ground. The leak rate measured on Artemis II was measured over 9 days. Nobody has measured what that hardware does over 30 days, or 60, or longer. Kshatriya's distinction becomes sharper here. He said the valves do not need to hold pressure the same way for a low Earth orbit mission, but that for a lunar orbit mission they do. A lunar station mission is the most demanding version of that requirement. The propulsion system must sit dormant in a punishing thermal environment for an extended period and then work perfectly when the crew needs to come home. That is not a burn you can attempt twice. I want to be measured here because the station's own schedule has been repeatedly revised and its final configuration is not settled. Building a plan on top of it is speculative in ways the rest of this story is not, but the direction of travel is clear enough. Longer missions, more time in the environment, greater dependence on propulsion performing after long dormancy. Every one of those trends increases the importance of the component that cannot be inspected, and every one of those missions will end the same way. The module separates at 400,000 feet, and everything it learned about itself burns with it. Part 33. The summer they could not get the rocket to launch. Before Artemis I ever left the ground, it tried twice and failed. The first attempt came in late August of 2022. The countdown stopped because of a problem with temperature readings on one of the 4 main engines. The second attempt came days later, at the start of September. That one stopped because of a hydrogen leak at a quick disconnect fitting, where a fuel line attaches to the rocket. Hold that phrase, quick disconnect, because it is the same family of problem we have been circling all night. A joint. A seal. A gas small enough to find any imperfection. Hydrogen is not helium, but it is the next smallest thing you can try to contain, and it behaves in much the same way. It escapes through fittings that would hold anything larger without complaint. Engineers replaced seals on the pad. They ran a tanking demonstration to prove the fix. Then a hurricane forced the rocket back to the assembly building. Artemis I finally launched on the 16th of November, 2022, months after the first attempt. Now I want to be careful about the lesson here, because there is a lazy version of it. The lazy version says the program is incompetent because it could not fuel a rocket. That is wrong, and anyone who has worked with cryogenic hydrogen will tell you it is wrong. Hydrogen at those temperatures is genuinely brutal to plumbing. Metal contracts. Seals stiffen. A joint that is perfectly tight at room temperature opens microscopically when it is chilled to hundreds of degrees below zero. The space shuttle had hydrogen leak scrubs too. So did programs before it. The honest lesson is narrower and more useful. Across 3 separate systems on 2 different vehicles in 2 different decades, this program has run into the same category of failure: hydrogen leaking past a fitting on the pad, helium valves needing replacement before both launches, and now helium leaking past a valve seat in space. Sealing small molecules is the recurring theme of this entire architecture, and notice the crucial difference between the pad problems and the flight problem. When a fitting leaked on the pad, technicians walked up to the rocket and replaced the seal. They could touch it, they could inspect it, they could test the repair before flying. The valve on Artemis II leaked 200,000 miles from anyone who could reach it, and then it burned. Same class of problem. Completely different access. That difference is the entire film. And it applies just as sharply to the hardware that has to land on the moon, which does not exist in flight-ready form yet. Part 34. The 2 landers that have not landed. Artemis cannot put anyone on the moon without a lander, and there are 2 under contract. The first is a version of SpaceX's Starship. The second is Blue Origin's Blue Moon. Let me describe the Starship approach, because the architecture is genuinely audacious, and its difficulty is routinely understated. A Starship cannot fly from Earth to the lunar surface on one load of propellant. It does not have the performance. The plan is to launch a Starship into Earth orbit, then launch additional tanker Starships, and transfer propellant from the tankers into the lander while both vehicles are in orbit. Public estimates of how many tanker flights this requires have varied widely, and NASA and SpaceX have given different figures at different times. What is not disputed is that it is more than a handful, and nobody has ever transferred cryogenic propellant between 2 spacecraft in orbit at that scale. Think about what that involves. You are moving liquid at extremely low temperature in weightlessness, where liquid does not settle to the bottom of a tank. You must connect 2 vehicles, open valves, and move thousands of kilograms of freezing propellant between them without losing it to boil off. That capability does not exist yet. It is the single largest unproven element in the entire program. NASA's Office of Inspector General reported in March of this year that SpaceX was more than a year behind on its critical design review, on the propellant transfer demonstration, and on the uncrewed lunar landing that must precede any crewed attempt. The propellant transfer demonstration was targeted no earlier than late this year. The uncrewed landing around the middle of next year. Blue Origin's position was different, but not obviously better. The company was still resolving mass and propulsion shortfalls on its Blue Moon Mark II vehicle, and nearly half the action items from its 2024 preliminary design review remained open a year later. Now put those 2 clocks beside the one we have been following. The valve redesign must be complete for Artemis IV in 2028. The landers must be proven for the same window, and a lander cannot be tested casually either. Every uncrewed demonstration costs an enormous amount and takes months to prepare. Here is what strikes me most about this comparison. The lander problems are visible. They are discussed in Inspector General reports, in congressional testimony, in every space publication. Everyone knows Starship needs to prove propellant transfer. The valve problem is not visible in the same way. It surfaced in a press conference, was reported for a few days, and largely disappeared. This whole story is about. The risk everyone can see gets attention. The risk in the plumbing does not. And the same asymmetry applies to the system that actually brings a crew down, which almost nobody thinks about until it fails. Part 35. 11 parachutes and no second attempt. Orion's parachute system is more complicated than most people imagine, and it is worth understanding because it illustrates how these vehicles are actually made safe. The full sequence involves 11 parachutes. 3 of them pull off the forward bay cover, the protective shell over the parachute compartment. 2 drogue parachutes then deploy to stabilize and slow the capsule. 3 pilot parachutes follow, and their job is to extract the 3 main parachutes. 3 mains, each 116 feet in diameter, bring the capsule down to about 17 miles an hour. Every one of those events must happen in the right order, at the right altitude, within seconds. Now, here is the part that matters for our story. The system is designed to work even when it does not fully work. Orion can land safely on 2 main parachutes instead of 3. The descent is faster and harder, but it is survivable. That is deliberate redundancy, and NASA proved it through an extensive qualification campaign involving dozens of drop tests, including deliberate failure cases where parachutes were prevented from opening. They dropped test articles from aircraft repeatedly, over years, in configurations designed to fail. I want to hold this up as the positive example in this entire film, because it is the exact opposite of the valve situation. The parachute system was tested to destruction, on the ground, repeatedly, in the failure modes engineers were worried about. Every test article came back. Every canopy could be inspected afterward. When something behaved unexpectedly, they could lay the fabric out on a floor and look at it. That is what a fully inspectable qualification program looks like, and it is why parachutes are not what keeps anyone awake. Now recall what we established about Artemis I. Fragments of heat shield material were liberating during entry and travelling down the body of the capsule, past the forward bay cover. The compartment underneath that cover holds this entire system. That is why the shield fragmentation was more serious than a thermal issue. A protective system tested exhaustively against its own failure modes was potentially exposed to a hazard from an entirely different subsystem. Systems that are individually safe can still interact dangerously. That interaction is exactly the kind of thing you discover by examining hardware after a flight, which works beautifully for parachutes, because they come home, and it works not at all for a valve, because it does not. The parachutes get dozens of tests and full recovery. The valve gets 1 flight and an incineration. Part 36. 4 days on a lifeboat. I have described the Apollo 13 accident, but I have not told you how those 3 men actually survived it, and the story explains why engineers trust hardware they can touch. The oxygen tank ruptured roughly 56 hours into the flight. The explosion crippled the service module and began draining the command module's power and oxygen. The command module was dying. Within about 2 hours it had to be shut down completely to preserve its remaining battery power for re-entry. So the crew moved into the lunar module. The lunar module was designed to support 2 men for around 2 days on the moon. It now had to support 3 men for around 4 days in deep space. It was never designed for this. There was no procedure. Nobody had planned for a spacecraft to be used as a lifeboat. And it worked, because engineers on the ground rebuilt the mission in real time using hardware they understood in physical detail. The most famous problem was carbon dioxide. The lunar module's scrubbers were being overwhelmed by 3 men breathing instead of 2, and carbon dioxide was climbing toward dangerous levels. The command module had spare filter canisters. They were square, The lunar module's fittings were round. Engineers in Houston assembled the exact inventory the crew had aboard, laid it out on a table, and built an adapter using plastic bags, cardboard, tape, and a hose from a spacesuit. Then they read the instructions up to the crew, who built the same thing. It worked. Carbon dioxide levels came down. I tell you this because of one detail that gets lost in the retelling. Those engineers could solve it because they had the physical objects in front of them. Not diagrams, not telemetry. The actual identical hardware, on a table, in their hands. They could pick up the canister and see that it was square. They could hold the hose and see whether it fitted. That is how engineering emergencies get solved. You get the object. Apollo 13 splashed down on the 17th of April 1970 in the Pacific. All 3 men survived, and the mission became known as a successful failure. Now hold that story against a valve that leaked 10 times worse than expected, and then ceased to exist. If something went wrong with that system on a future flight, and engineers gathered in a room to solve it, they could not put the component on the table. They could put a similar one there. A ground unit. A twin. And that twin has already been proven, by a factor of 10, to behave differently from the article that flew. Part 37. The 3 dishes that hear everything. Every piece of telemetry we have discussed reached Earth through one system, and it is worth understanding because it is the thread the entire argument hangs from. The Deep Space Network consists of 3 complexes spaced roughly evenly around the planet. One in California, one in Spain, and one in Australia. The spacing is deliberate. As Earth rotates, a spacecraft that sets below the horizon at one complex rises at the next. Something is always listening. Each complex has large steerable dishes, the biggest of them 70 meters across. Now consider the scale of what these dishes do. A spacecraft in deep space transmits with a power output comparable to a household light bulb. By the time that signal crosses hundreds of thousands or billions of kilometers, it arrives almost unimaginably faint. The network pulls those signals out of the noise. It is one of the most impressive pieces of infrastructure humanity operates, and almost nobody knows it exists. Everything we know about the helium leak came down that path. The pressure readings, the thermal test data from those repurposed hours when the crew pointed the spacecraft toward and away from the sun. Every number engineers will use to redesign that valve. All of it arrived as a faint radio signal, captured by a dish, decoded on the ground. And here is why that matters for this story. Telemetry is not a photograph of a component. It is a stream of numbers describing what sensors observed, at whatever sampling rate the designers chose, measuring whatever parameters they thought to measure years earlier. If a sensor was not installed at a particular point in the plumbing, that point produced no data. Not bad data. None. The design decisions that determined what could be known about that valve were made long before anyone suspected there would be a question worth asking. That is the deepest limitation of the telemetry argument, and it is not solvable by better antennas. You can build a larger dish and hear a fainter signal. You cannot retroactively install a sensor on hardware that has already burned. The Deep Space Network can hear a light bulb across the solar system. It cannot tell you whether a valve seat had a scratch on it, and that distinction is where this entire story finally comes to rest. Part 38. The belts they had to fly through. There is a hazard on the way to the moon that Artemis II had to cross twice, and it has nothing to do with valves. Earth is wrapped in 2 enormous zones of trapped radiation called the Van Allen belts. They exist because Earth has a magnetic field. Charged particles streaming from the sun get caught by that field and held in place, spiraling back and forth along the magnetic lines. The inner belt sits relatively close to Earth and is dominated by high-energy protons. The outer belt sits much further out and is dominated by electrons. Anything travelling from low Earth orbit to the Moon must pass through both. The International Space Station never does this. It orbits below the belts, which is one reason astronauts can stay aboard it for months at a time. Apollo crossed the belts. Artemis II crossed them, outbound and inbound. Mission planners handle this the way you would expect. You choose a trajectory that crosses the thickest regions quickly, at an angle that minimizes exposure, and you accept a dose that is measurable but tolerable. Artemis I carried radiation experiments specifically to characterize what a crew would receive, including instrumented mannequins in the seats fitted with thousands of sensors. That is genuinely good practice. Fly the hazard uncrewed first, measure it, then decide. But hold this alongside everything else, because there is a connection people miss. Radiation does not only affect people, it affects electronics. High-energy particles striking a microchip can flip a bit, corrupt a memory location, or in rare cases damage a component permanently. Spacecraft avionics are hardened against this, and critical systems are made redundant, so a single upset cannot take down a function. Now think about where the propulsion control electronics live. They live in the module that burns. If a radiation event had degraded a valve controller or corrupted a sensor reading, the physical evidence of that damage would follow the same path as everything else, down to 400,000 feet, then into the atmosphere, then gone. I am not suggesting radiation caused the helium discrepancy. There is no evidence for that, and I will not manufacture any. I am pointing out that the list of things that could explain a 10 times discrepancy is long, that several of the candidates leave physical traces, and that no trace of any kind survived the flight. The environment out there is harsh in more ways than temperature alone, and sometimes it becomes far harsher with almost no warning at all. Part 39. The storm that arrives without warning. There is a risk on lunar missions that is genuinely frightening and almost never discussed outside the field. The sun occasionally throws out a burst of high-energy particles. These events are called solar particle events, and the largest of them are dangerous to anyone outside Earth's magnetic protection. Here is the part that should get your attention. The warning time can be very short. A large event can begin affecting a spacecraft within tens of minutes of the eruption being observed. There is no meaningful opportunity to shelter somewhere else, because there is nowhere else to go. In August of 1972, a major solar event occurred between the Apollo 16 and Apollo 17 missions. Between them, Apollo 16 returned in April, Apollo 17 launched in December. The event fell in the gap. Estimates of what that event would have done to a crew on the lunar surface vary considerably, and I want to be careful not to overstate it, but the range of serious estimates includes outcomes from severe radiation sickness upward. The program flew 9 crewed lunar missions, and one of the largest solar events of the era landed in a window when nobody was out there. That is not planning, that is luck, and the people involved have acknowledged it as such. So what does a modern spacecraft do about it? The approach is a storm shelter, rather than shielding the entire vehicle, which would be impossibly heavy. You designate a region of the spacecraft and surround it with mass that is already aboard. Stowage bags, water containers, equipment. The crew rearranges the interior to build a temporary shielded volume and stays inside it until the event passes. Artemis II carried a demonstration of exactly this concept, and part of the mission involved evaluating how quickly it could be assembled. Now connect this back to the propulsion system, because the connection is direct and uncomfortable. If a severe solar event occurred during a lunar mission, the crew's priority would be to get home as quickly as the trajectory allows. Getting home quickly means burning the engine, which means the system that depends on those helium valves becomes the thing standing between a crew and a prolonged radiation exposure. On Artemis II, that scenario never arose, and the free return meant the engine was not needed anyway. On a mission in lunar orbit, with a crew that must burn to leave, the valve that leaked 10 times worse than predicted sits directly in the escape path. That is not a prediction. It is a description of where that component sits in the chain of things that keep people alive, and when a crew does come home, the last stage of that chain is a ship waiting in the ocean. Part 40. How you catch a spacecraft in an ocean. Recovering a capsule sounds like the simple part. It is not, and the way it is done reveals how much of this program depends on being able to physically retrieve things. The vessel used for Artemis II was the USS John P. Merthyr, an amphibious transport dock. Ships of that type have a well deck. The stern floods with seawater so landing craft can drive straight in. That is exactly what it is used for here. The ship partially floods its well deck, and the capsule is drawn inside on a line. Then the water is pumped out and the spacecraft settles onto a cradle. You are, in effect, driving a ship around a spacecraft and closing it inside. Divers reach the capsule first. They attach flotation collars and a stabilizing ring, then run tending lines to control it in the swell. And they inspect. On Artemis II, divers photographed the heat shield underwater before recovery, which is why we had images of that surface within hours rather than days. Now think about the timeline of certainty this creates. Splashdown occurred in the evening of the 10th of April. Underwater imagery of the shield existed almost immediately. NASA published an initial assessment on the 20th of April, 10 days from landing, to a public statement that the thermal protection system had performed as expected. That speed is only possible because the object came back. Divers can swim under it, cameras can photograph it, engineers can walk up to it in a hangar. The precision matters too. The capsule landed 2.9 miles from target, which meant the recovery force was already essentially in position. Compare that to what the propulsion investigation gets. No recovery ship, no divers, no photographs of the component, no hangar inspection 10 days later. The last data point about that valve is a number that arrived by radio before separation. There is no follow-up. There will never be a follow-up. 2 systems on the same spacecraft on the same flight, and one of them received a complete post-flight examination within days, while the other received nothing at all and never will. That asymmetry is not a criticism of anyone. It is the architecture doing exactly what it was designed to do, and it is about to repeat itself on hardware that is already being built. Part 41. The shield that flies next. I want to end the technical portion of this story where it began, with the heat shield, because there is a piece of this that is still unresolved. The Artemis II shield flew a shortened skip entry specifically because of the permeability problem. NASA has been clear that the trajectory change was the mitigation. The shield itself was not redesigned for that flight. The material was the same material. So what happens on the next one? NASA has said the Avcoat production process for later shields is being changed to address the permeability variation directly. The intent is to make the material's ability to vent gas more uniform, so trapped pressure cannot build in the way it did on Artemis I. That is the real fix. The trajectory change was the workaround, and everyone involved has described it that way. Now here is what strikes me about that. The heat shield gets a genuine materials fix, on the ground, verifiable by test, on hardware that can be inspected before and after every flight. Engineers can cut samples from a new shield and measure permeability directly. They can run ArcJet tests and compare results. They can fly it, recover it, and examine what actually happened. There is a complete feedback loop. Build, Test, fly, recover, examine, improve. That loop is why the heat shield problem is, in engineering terms, solvable. It took 2 years and enormous effort, but the path from problem to verified solution existed at every step. Now look at the valve. Build, test on the ground, using rigs already known to be wrong by a factor of 10. Fly, measure by radio. Destroy, there is no recover step. There is no examine step. The loop has a hole in it, and the hole is permanent. That is the difference between the two problems on this spacecraft, and it is the reason one of them got resolved in 2 years, while the other one has no published schedule at all. The shield taught this program something. It taught them that a 2-year investigation, with samples in hand and test articles to destroy, produces a real answer. The valve cannot be taught the same way. Not because anyone is unwilling, but because the method requires an object, and the object is gone. Which brings us all the way back to a capsule falling toward the Pacific in April, and to the question I still cannot answer. Part 42. What the shield taught us that the valve never can. On the 10th of April, 4 people came home from the moon in a capsule called Integrity. They landed 2.9 miles from target at a velocity within 1 mile an hour of prediction. By every reasonable measure, it was an excellent flight. The heat shield the world had spent 2 years worrying about performed better than Artemis I. The trajectory fix worked, the engineers were right, and the administrators' confidence was justified. The dissenters were not vindicated by events, and they were also not wrong to speak. A program where nobody writes that letter is more dangerous than one where somebody does. Everything visible worked, and it worked because attention was pointed directly at it. The one thing that did not behave as predicted was a valve. It sat inside a module already scheduled for destruction. It leaked 10 times worse in space than on the ground. It will now require what NASA itself calls an extensive redesign, and no human being will ever examine it. So let me give you the precise version of that, because precision is what this deserves. Nothing catastrophically failed aboard Artemis II. The word failure is too strong, and I have tried not to lean on it. A known leak behaved worse than expected in an environment nobody could fully simulate, but the second half of that sentence is literally true, with no exaggeration in any direction. The physical object that leaked was destroyed on purpose. It happened roughly 20 minutes before 4 people came home, at 400,000 feet. It will be destroyed again on the next flight, and the one after that. It will happen on every crewed Orion mission for as long as this architecture flies. They took a deposition from it in its final days. They pointed the spacecraft toward the sun and away from the sun, and recorded everything. They understood that within the week, the witness would be gone. That is what engineers do when the evidence has an expiry date. And here is the question I cannot resolve, though I have looked hard for a way. Can you actually repair something you are never permitted to examine? NASA's answer is yes, and it is a serious answer deserving respect. Telemetry is real data. Flight characterization is genuinely useful. Aerospace has reasoned about destroyed hardware since the beginning. Columbia's investigators proved a foam strike by firing a cannon at a wing in San Antonio. The counter-argument is equally serious. Those investigators could rebuild the event because they knew the conditions. Here, the conditions are the unknown. Ground and flight behavior differ by a factor of 10, and nobody has fully explained the gap. You cannot reconstruct a failure whose driving conditions you have not yet identified. I do not know which of those is right. Anyone who tells you they know is selling you something. What I know is that the answer arrives in 2028. It arrives on a mission that needs the engine at the moment of lunar orbit insertion, and whatever we learn, will be learned from a machine already falling toward its own incineration. Every accident tonight was preceded by a stretch where nothing went wrong. That is the mechanism. Every single time. Foam came off 65 times out of 79, and the shuttle came home 65 times. O-rings eroded, and the boosters worked anyway. A tank fell 2 inches and flew for 18 months without complaint. The signal was always present in the data. It was simply outranked by the absence of consequence. The most dangerous stretch of any program is not the moment everyone is frightened. Fear produces Inspector General reports and independent review teams and open letters. Fear is protective. The heat shield received 2 years of fear, and the heat shield came home clean. The dangerous stretch is the one that follows. When the thing everybody feared turns out fine and the fear disperses and attention moves to the next visible problem. Somewhere in the plumbing of a module being assembled in Bremen right now, there is a valve, a redesigned one, or a modified one, or possibly the same one with a tighter specification. It will fly toward the moon in 2028. It will be asked to hold full pressure for the first time that matters. And then, 20 minutes before the crew comes home, it will burn.